Okay. Good morning, everyone, and welcome back to the Complex Dynamic Week. Today we are going to start with a talk of Professor Hongming Nie, who got his PhD at Indiana University under the supervision of Kevin Pilgrim, and now he's working as a midnight lecturer at Stony Brook. He he's going to talk today about the boundedness of hyperbolic components for Newton maps. So, Professor, whenever you're ready.
Okay, thank you, Alex. Yeah, thank you for giving me this good opportunity to show my work on complex dynamics. Yeah, it's the very early in Peru, so right, okay. Anyway, yeah, so today I would like to talk about some boundedness of hyperbolic components for Newton maps. Okay, this is a joint work with Yan Gao from Shenzhen University. Okay. Okay, first let me fix some notation. So we fix D and list 2 and write D to be the space of degree D rational maps in one complex variable. And write MD to be the modular space of degree D rational maps, which is the quotient space of D by the Mobius transformation. Here we modulo the Mobius conjugacy. So the right D is an open and dense subset in the 2D plus 1 dimensional projective space. So considering the coefficients of a rational map in right D, so we can write a rational map in right D to be the quotient of two polynomials. Then we consider the coefficients of the two polynomials. Then we get the map from right D to P2D plus 1. So then the right D is a non-compact manifold, but the MD is a non-compact orbifold. Okay. So now we want to give a compactification for these two space. So first of all, right D is very natural to compactified by the P2D plus 1. So for any element in 2D plus 1, but not in right D, it can be written as a quotient of two polynomials, such that these two polynomials has a common root, or the maximum degree of these two polynomials is strictly less than D. So this is the compactification for right D. So for MD, so it kind of harder to give a compactification, but we can use the geometry invariant theory to compactify MD. So okay, this compactification is slightly different for even D or for odd D. So here we consider, okay, to make it easier, we just consider even degree. Then the compactification of MD is the quotient of right ds, where right ds is the stable points in P2D plus 1. Roughly, so for any point in right ds, it can be written as the quotient of two polynomials, such that the each common root of these two polynomials has multiplicity at most D over 2. Okay, this compactification is given by Silverman. So for general D, using a different method, Milner gave a compactification for the quadratic case. So there is some other compactifications for MD. So for example, DeMarco gives some compactification using the barycentered measure of max entropy. Okay, here in this talk we will take the geometrically invariant compactification. Okay, so then we consider boundary. The boundary MD, sometimes called the boundary of MD and the infinity. Okay, so this talk we focus on hyperbolic rational maps. So the definition for hyperbolic is that so a rational map is hyperbolic if each correct point is attracted to an attracting cycle. So here is an example of hyperbolic rational map or hyperbolic polynomial. So we consider the polynomial z squared plus c, where c is roughly minus 0.123 plus 0.745i. Then we have in the middle for the component that the correct point, this correct point is attracted to a 3 cycle. Okay, so this is an example for hyperbolic polynomial. So the hyperbolic maps from an open set in right D, which give us an open set in MD. So each component is a hyperbolic component. So so we let H be a hyperbolic component in MD, and we consider the closure of H in the MD bar. So we say H is bounded if the closure of H does not intersect with the boundary of MD. Otherwise, we say H is unbounded. So in other words, so H is bounded if H is precompact in MD. So the interesting question is to ask which hyperbolic component in MD is bounded. So this question can also ask in some natural slice of MD. So if we know the bounded hyperbolic components and we know the unbounded hyperbolic components, then we may ask the boundary of unbounded hyperbolic components. Okay. So here is the first, the baby example. Let's consider the polynomial, the quadratic polynomial, z squared plus c. So the manifold set is defined to be the parameter c, such that the unique quadratic point 0 has a bounded orbit. So the black region in this picture is the manifold set. Okay, so then any component in the interior of this black region is a hyperbolic component, and it's obviously it's bounded. So the orange region, which is the complement of the manifold set, is also a hyperbolic component. This hyperbolic component is unbounded. Okay, this is the first example for quadratic polynomial. Now so this example is a one-dimensional case. So for higher dimensional, the Makinko gives some sufficient conditions for unboundedness. So the first bounded result in the whole space. Oh, sorry, here should be M2. So it's given by Epstein. He showed that so in M2 in the modular space of quadratic rational map, the hyperbolic components with 2 distinct attracting cycles of period and at least 2 are bounded. So in his case, so the modular space of quadratic rational map is biholomorphic to C2. So as we know, the quadratic rational map has 2 quadratic points. So it has at the most 2 attracting cycles. So Epstein shows if the attracting cycle has the maximum number, then the hyperbolic components are bounded. So with Kelvin Pilgrim, we extend the Epstein result to biquadratic rational maps. So in our result, we don't have the requirement on degrees, but we still require that only 2 quadratic points. Count without multiplicity. So So very recently, so Feynman and Pilgrim studied some non-trivial unbounded hyperbolic component in the modular space of quadratic rational maps. I should do remark here that so in the result, in absolute result, and in our result with Kevin, so we require the number of attracting cycle equals to the number of critical points. So this kind of hyperbolic components is called of type D. So such hyperbolic component has a very nice algebraic structure. So in the result with Kevin, we use some non-Archimedean techniques to give the proof. So anyway, I will talk this later. Okay, this is a null result in higher dimension. So in this talk, I will focus on Newton maps. So what is a Newton map? Given a complex polynomial P of degree D with distinct root. So its Newton map is the rational map given by Fp, which is Z minus Z over P, P Z over P prime Z. Here we require the polynomial has distinct roots because we need the degree of Fp equal to the degree of P, which is D. Okay, so then the other, the basic property for the basic dynamical property for Fp is that the fixed point of Fp are the roots of P, and all these fixed points has multiplier. The degree. The derivative is 0, so they are super attracting, and the point infinity is a unique repelling fixed point of Fp. So we can calculate the critical point of Fp, which is just we take the derivative of Fp and set it 0. We get the root. The solutions are the root of P and the root of the second derivative of P. Okay, so we just call the root of the second derivative of P to be the additional critical point of Fp. Okay, in our later discussion, we will more focus on the additional critical point. Okay, this is an example for Newton maps. We consider the polynomial Pz equal to Z times Z minus 1 times Z minus I. Then this is a dynamical plan for the Newton map Fp. So it has three. Okay, in this picture, it has three fixed point, which is roughly the center of the gray region and the center of the green region and the center of the red region, which is I0 and 1. Okay, that is the additional critical point. This example is 1 plus I over 3, which is in the green region. Okay, so all the small, for example, all the small red factor component will eventually map to the bigger red factor component. And same thing for the gray factor component and the green small green factor component. Okay, this is an example for Newton map. So now we consider the modular space of Newton map. So we let MD to be the space of degree D Newton map. Okay, remember here we always require the Newton map has distinct roots. The modular space of the degree D Newton map is MD quotient the affine maps modular the affine conjugacy. We denote ND by the modular space of degree D Newton map. As we said before, the infinity is the unique rebellion fixed point. So here we only need to quotient the NMD by R to C. Okay, because we need to fix the fix the point at infinity. So okay, here are some remarks for the modular space of Newton map. First is the dimension of the space of degree Newton map is D, and the dimension of the modular space of degree Newton map is D minus 2. Okay, because for any Newton map, it's uniquely determined by its roots. So for degree Newton map, it has D roots, so the dimension of NMD is D, and the dimension of ND is just D minus 2. So in the when D is small, for example, if D is 2, then the N2 is a singleton. In fact, for quadratic Newton map, we can always conjugate this map such that the root of the Newton map is 0 and 1. Okay, we can always do that. So the space N2 has only one element. Okay, the set N3 is isomorphic to C. So as the case for N2, so we can always conjugate the 3 root to 0 to 1 and some other root, and this root gives us the parameter. Okay, this is a cube case. So we consider the polynomial PAZ, which is z minus 1, z minus over 2 minus a, and times z minus 1 over 2 plus a. Okay, so then the correct points for the Newton map of PA is 1, minus 2, minus 1 over 2 minus 1, and minus 1 over 2 plus, minus 1 over 2 minus a, and minus 1 over 2 plus a, and 0. So the first 3 correct points are just the fixed point, and just the root of the Newton map, and the point 0 is additional correct point for FPA. Okay, so the color in this picture is determined by the orbit of 0. I mean, the orbit of the additional correct point. So if the additional correct point 0 is attracted to 1, then it's colored by red. If it's attracted to 1 over 2 minus a, it's colored by blue, and if it is attracted to minus 1 over 2 plus a, then it's colored by green. So if we zoom the small piece here, then we will get the right the picture on the right hand side. So there is some small black region here. So for this region, so the additional correct point is not attracted to any root. Okay, in fact, here is some phenomena called the luminization. Okay, this is the parameter space. Roughly the modular space of cubic for cubic Newton maps. Okay, so Roach 1 and Yin prove that for cubic Newton maps, there is a unique unbounded hyperbolic component, and all other components are bounded with Jordan curves boundaries. So let's look at this. Let's look at this picture again. So this plan is not the modular space of cubic Newton maps, but so if we consider the modular space, it's just map this picture. Okay, it's the red region, the big red region, and the blue region and the green region will glue together to quotient together to get one component in N3. Okay, and this gives us the unbounded component. Okay, this is the boundedness of hyperbolic components in N3. Okay, in this talk, we will consider the hyperbolic component in N4. Okay, for quartic Newton map, it has, totally 6 credit points. 4 of them are the roots of the Newton map, and 2 of them are additional credit points. Okay, so then there are several cases for the orbit of these 2 credit points. The first one is at least one of the additional credit points in the immediate basin of a root. Okay, the second case is there are 2 attracting cycles, and each of them have period at least 2. Then there are several other cases. For example, the both additional credit points in the basin of one attracting cycles of period at least 2, or both attracting additional credit points are in the basins of root, but not in the immediate basin of root. So I should mention here that if a Newton map has a any Newton map has a attracting cycle which are not fixed, then this attracting cycle, okay, let me see how to show this one. Okay, so I should see that. Okay, any period 1 attracting cycle for Newton map is fixed point. So which are super attracting fixed point, which are the roots of the Newton map. So we are more interested in the period and at least 2 attracting cycles. Okay, let me give some examples for these cases. So, this picture gives an example for Newton map in a hyperbolic component, such that at least 1 additional credit point in the immediate basin of a root. So, in this picture, so the additional credit points are 0, 0, and 7 over 4. Okay, it's very small here. So the 0, in fact, is an additional credit point. It's also a root. So which means 0 is fixed. So another additional credit point, 7 over 4, is mapped into the immediate basin of 0. Okay. So the hyperbolic components containing 7 over 4 is mapped to the hyperbolic component, mapped to this big blue photo component. Okay, sorry, I should say, the photo component containing 7 over 4, this tiny blue one is mapped into the photo components containing 0. Okay. So this is an example of Newton maps in hyperbolic components such that it has 2 distinct attracting cycles. Okay, so in this example, the 2 additional credit points are 0 and roughly 1.3. So the additional credit point 0 has orbit 0 maps to 1, then go back to 0. And the credit point 1.3 maps to A, then A maps to go back to 1.3. Okay, I didn't calculate this number A, but I just track the orbit for the credit point. Okay, so for the other cases, so I just give 2 examples. On the left one, it's a Newton map with 2, the 2 additional credit points for the left example is and 0 and 1. Sorry, it's and 0. Okay, 0 is a multiple credit point. Okay, so and 0 maps to 1. Okay, the 1 is very tiny here, maps to 1, then 1 maps to 0. Okay, so this example shows that there exists hyperbolic Newton map such that both additional credit points are in the basin of 1 attracting cycle. So the example in the right hand side, in the right is a Newton map. Okay. I think okay. I think I made a mistake. Okay, I think these are the same picture. Sorry. So okay, I should say okay. There exists a Newton map, such that it has two additional quadratic points. I mean, at one minus one and one such that okay, one little quadratic point maps to another one, and another one maps to a root. Okay, I should. Okay, sorry, I made a mistake for the pictures. Okay, this shows all these three cases happens for I mean in N4. Okay, so now let's consider the boundedness of this hyperbolic components. So the first case is called type IE, which means the immediate escape. So this is unbounded. So with Kelvin ratio, the type IE components is unbounded. We use some quasi-conformal deformations and the Peterson-Lewis idea on convergence of rational rays. Okay, so for the second case, so if there are two distinct attractive cycles and each of period and at least two, so this hyperbolic components are of type D, which means disjoint because it has two distinct attracting cycles. Okay, so for this hyperbolic components with Kelvin ratio, they are bounded. Okay, this is from, it's based on absolute work on type D components for quadratic rational maps and KV's result on KV's and non-Archimedean techniques on rescaling limit. So in this case, the type D components have good structures, which means these components are semi-algebraic. So then we can consider, instead of consider the sequence, we can consider, the analytic families. So, and we also use there are two distinct attracting cycles to run the argument. So, okay, so it means, okay, these two pieces, the good structure and the two attracting cycles are required to run the argument. Okay, so now for the other cases, this is different from the type D case because there has no two distinct attracting cycles. So, okay, so the first result is shows with the Yang-Gao, we prove all other cases are bounded. This means all the other cases in the case 3 are bounded in N4. In other words, it means okay, hyperbolic component H in N4 is unbounded if and only if H is of type IE. Okay, just recall that a type IE component means every element in this hyperbolic component has at least one additional quadratic point in the immediate basin of a root. Okay, this is the only case of unbounded hyperbolic component. Okay, this is a slice in M4 in the space of space of quartic Newton maps. So okay, so we require every element in this picture has a quadratic point which are in two cycles. Then all the components indicate A, B, C, D, and FE. FE1 are bounded. In other words, only the components indicated with IE are unbounded. I mean, in M4, in N4. Okay, so the latter, is indicated. According to the orbit of additional credit points. Okay, so okay. So let me give some remark on this boundedness result. So in cubic case, Roche and Wang Yin shows okay the type RE component is unbounded, and the type RE component if a hyperbolic component in N3 is unbounded if and only if it's type RE, so we can also define the type RE, in N3, and that's a unique such component. So for quartic case, our argument heavily relies on the number of additional credit points. So because we will, control the orbit of this additional credit points. So for higher degree, so with Kevin pictogram, we show type RE components are unbounded. Okay, in general. But for the reverse implication, we don't know. It means we don't know if, for higher degree case, we don't know if we don't know is unbounded component type RE. Okay. So let me give the main idea to show this result. Okay, here I just give the idea to show one direction, to show the non-type RE implies bounded. Okay, let's pick a non-type RE component in N4. Okay, so then there are lots of cases by the orbit of the additional credit point. To make it easier, we assume the hyperbolic component H has an attracting cycle of period under these two. So it is, similar to show the case when it has no, attracting cycle of period under these two. Okay. So now let's suppose this hyperbolic component is unbounded. Then we take a sequence in this hyperbolic component and assume this sequence is degenerating. Now let's consider a lift F1 in NM4 such that this F1 has no root cladding. Then okay, the limit. Now we consider the limit F infinity of F1 in P9. Okay, Pauling subsequence, we can also consider this limit. So this limit F infinity induces a Newton map F infinity height of degree 2 or 3. So remember that so the F infinity is just a point in P9. It is not a Newton map, but we can cancel the common roots in the numerator or denominator, and we get a rational map, which is in fact a Newton map of lower degree. So now the case step is we need to bound the immediate basin of a attracting cycle. Okay, and show under a finite iteration of credit point, and show a finite iteration of credit point is close to infinity for n sufficiently large. Okay, if we finish step 3, then we can get a contradiction. So here is a point to rule out the limit, the case that the limit has degree 2, which will rule out this case. For non-type RE components, it's not hard to rule out such case. Okay, so I will say how to rule out the quadratic limit. So before that, I should mention here that the key point is to bound the immediate basin of the attracting cycles for F1. So to do that, we prove the convergence result of graphs for Newton maps. So let's give any graph gamma infinity of f hat infinity, and which is which consists of the plane images of internal rays. Then under some natural assumptions, there exists a graph gamma n for f1 such that the gamma n is homomorphic to gamma infinity and gamma n converges to gamma infinity as n goes to infinity. Moreover, the dynamics of f1 on gamma n is conjugated to the dynamics of f infinity hat on gamma infinity. In other words, so the gamma n is a perturbation of gamma infinity and roughly preserves the dynamics. So here the natural assumption is about the perturbations of internal rays. We need the perturbation, such perturbation lines on the boundary of photon components, and the landing points don't meet the critical points in their forward orbits. Okay, we just this assumption is to guarantee the gamma n is a graph. Okay, roughly is a connected graph if gamma infinity is connected. Okay, so here is an example of the perturbation of internal rays. So the on the left is the red lines are internal rays for a cubic Newton map. So okay, it's on the left. It's a Newton map which is very close to the Newton map in the left. So look at here. So the C, the critical point C on the left is in the Julia set, but its perturbation Cn on the right is in Fatou set. Okay, so if internal ray does not land and C on the left, then its perturbation will give us a internal ray. The perturbation of such internal ray will land on the Julia set. So if the internal ray on the left, lands and C, then its perturbation will, lands and C, but it's not on the Julia set. So in other words, roughly, so the perturbation, if the convergence of the Newton map, is good enough, then the perturbation of the internal rays is either lands and the Julia set or lands some, integrated plane images of credit points. Okay. Okay, so now in this convergent result, we're also working on the graphs. So here is two examples of graphs. The first one is called the Newton graph, which is studied by Dirac, Lodge, Mechanic, Rochter, and Slasher. There's another graph. It's called the graphs from cut angles, studied by Roche. Okay, here is an example for specific Newton maps with these two graphs. So the Newton graphs is constructed for the following. Okay, we consider the fixed internal rays in the emitter basin of loops. Then we consider the plane images and consider the connected of the plane images containing the fixed internal rays. Then consider the plane images in the next level. Then we will get the Newton graph. So in this picture, so the black curves is a Newton graph. So all the in fact it has level 1. So it's just the plane image of the fixed internal rays. So the graphs from cut angles is mainly to consider the different photon components. Intersecting at some common boundary. Then we can construct a graph through this common boundary. So in this picture, the right curves is a graph from the cut angles. So the numbers close to this segment, it gives the angles in the angles for the internal ray. Okay. Okay, so okay, now as I mentioned, in this case, it's not hard to rule out the quadratic limit. How to do that? So if the limit is quadratic, then okay, because we know the limit is a Newton map, then up to Mobius conjugate is conjugate to Z square. Then we consider all the rational rays of f hat infinity and consider perturbations for the single rays for f1. Then we can conclude that Fn had two root infinity basins share boundaries and the common angles and the rational angles, which is possible. So let's look at this picture, this example. So it's a Newton map, not in the type IE components. So any two root infinity basin cannot share boundary and the rational angle. Okay. So this is the way to rule out quadratic limit. Okay. Now let me give the sketch of the proof for the bounded result. Okay. So now, okay, because we assume there exists a limit that exists an attracting cycle denoted by On for F1. So the first step is to show, okay, this attracting cycle. Okay, so the first step is to show the limit of this attracting cycle is still a cycle in C. Okay, there is still a cycle at the limit of On. Now we construct a curve in the Newton graph. So surround the limit cycle O. Okay, then under the convergence result, so we can get a closed curve around the cycle On, and this curve, this perturbation is bounded. So, but that's the case. That's the last step is to show some credit point under certain iteration, okay, which is very close to infinity. But we already know, so all boost credit points will eventually bounded by the perturbation of the perturbation of the curves constructed. So this gives the contradiction. This means the non-type IE components are bounded. Okay. Okay, so this is the bounded hyperbolic components. Now, okay, next we will consider the boundary of unbounded components in N4. Okay, let's first recall the compactification of MD. So where MD is the modular space of degree D rational maps. So the modular space of quartic Newton map is a subset of MD. Then the closure of N4 is a compactification of N4. The closure of N4 in MD bar is a closure of N4. So we denote by N4 bar. So okay, more precisely, so we can find out the N4 bar is just the disjoint union of N4 and N3 bar and N3 prime bar, where N3 is just the modular space of cubic Newton maps, and N3 prime is the modular space of Newton maps for quartic polynomials with a multiple roots, okay, with a unique multiple roots. Okay, so and the AM3 bar is the one-point compactification of N3 and N3 bar. N3 prime bar is a one-point compactification of N3 bar. So in fact, okay, the boundary of N3 is just a point. Okay, a point of a quadratic rational map. In fact, the quadratic Newton map. So the boundary of n.
Tu me tiens au courant?
Sorry. Okay, the boundary of n prime q n prime 3 is a Newton map of degree 3 with multiple root. Okay, so now recall that the bounded hyperbolic components in M4 is type IE component, which means some roots of immediate basin contains at least 2 correct points. Okay. Now there are 2 cases for such type IE components. Okay. So let's suppose there's only one immediate one root immediate basin containing 2 correct points. Okay, let's denote it by omega 0. So now let's consider the correct point which are not in omega 0. Okay, and consider its orbit. There are 2 possibilities. One is the orbit of the correct point not in omega 0 does not meet the complement of omega 0 containing 1 root. Okay, this is an example on the left. Sorry, on the left. Yes, on the left. Okay, so that's another case is that the correct point that not in omega 0 and its orbit intersect with the component of omega 0 containing 1 root. Okay, because omega 0 is a root unit basin containing 2 correct points, then it separated its complement has 2 complement components. So and one is containing 1 root and one is containing 2 roots. Okay, so if the additional correct point which not in omega 0 has fourth orbit maps to the one intersect the one containing 1 root, then we call it type IE. Okay, so on the right is an example of a Newton map in a type IE component. Okay. So now let me state the boundary of the unbounded components in N4. So let's use the notation partial infinity H to be the boundary, the intersection of boundary H intersects the boundary of N4, which is the boundary of H and infinity. So if H in N4 is an unbounded hyperbolic component, then the boundary of H and infinity is connected. More precisely, so if H is not of type IE, then if H is not of type IE, then the boundary of H and infinity is the closure of a hyperbolic component in N3 bar. If H is of type IE, we should further assume the boundary of H is contained in N3 bar. Then the boundary of H and infinity is a singleton of a cubic Newton map with a prefix Julia correct point. So in other words, so let's consider the hyperbolic components containing the Newton map on the left on this picture. Then the boundary of the hyperbolic component containing this Newton map and infinity is a closure of a hyperbolic component in N3 bar. Okay, so for the hyperbolic components containing the Newton map on the right, so if we assume the boundary and infinity is contained in N3 bar, then it should be a singleton. Okay. Okay, I will give some remark on this result. The first is, okay, if we consider the center of the limit of the boundary, the boundary and infinity, then it has a unique additional credit point. In fact, this additional credit point has the same portrait of its perturbation for the center of H. Okay, so if in the case 2, if H is of type IE, then we write omega to be the root of the root immediate basin of F having degree 3. Okay, that is a unique such root immediate basin, and we denote K1F to be the component of C minus omega containing a unique root, and let L to be the smallest integer such that the L's forward image of C lying K1F for a credit point C. Okay, in fact that the credit point C is unique. Then for the limit for the point in the boundary partial infinity H, so its L's interval of the credit point of the additional credit point is infinity. Okay, so now okay, I should explain why we need the assumption in case 2 that the AM3. Okay, I will explain it. Okay, before that, I just gave the sketch of the proof for connectivity. Okay, let's assume H for any element in H has a root immediate basin of degree 3. So then we consider the Blaski model, which is conjugate. Consider the Blaski model for F in this root immediate basin. Then we have this formula for the Blaski product. So now the K proposition is that for any sequence in H, so passing subsequence if necessary, then this sequence is degenerating if and only if this sequence has a lift such that this lift has no loss collision and the corresponding parameter in the Blaski product convert to 1. Okay, so under this proposition, so to show the connectivity, we construct some suitable curves in the Blaski model and check the stability of the limit. So here we should be careful here that because some limit for these curves, some point for the limit in the limit of these curves may be unstable. So we should do some conjugacy to check the limit is connectivity. To check the limit is connected. So okay. So as long as we know the connectivity of the limit, we will show more the detailed classification for this limit. Okay, now let me explain why we assume the partial infinity H is contained in AM3 bar. Okay, so in fact if H is not of type IE, then we can show the boundary of H and infinity is contained in AM3 bar, which means okay, we can write the quadratic limit if H is not of type IE. Okay, so so this is the example we see in previous slides. So this is an example for for Newton map in a non-type IE component. So in this case, so we know the root basin omega 1 will convert to infinity. So we can show that for non-type IE component, but we cannot do that we cannot show that for type IE component. Okay, so to show the non-type IE components has bounded and infinity contained in N3 bar. So we need 3 pieces. The one is topological theory, and okay, the second is the characterization of post-critically finite Newton maps, which is due to large Mach and Stretcher. And we also need the rigidity of Newton maps, which is due to the rush and Stretcher. Okay. Okay, so now let me show how to rule out the quadratic limit for non-type IE component. Okay, the first step is to do the theory. So, okay, applying the topological theory, we can construct some quartic Newton map from a given cubic Newton map. The detail is that, okay, pick any f in N3, okay, in the modular space of cubic Newton map. If f is post-critically finite, okay, let's suppose f is post-critically finite. Okay, if f is hyperbolic, then there exist finitely many non-type IE hyperbolic components in N4. Okay, M4 should be N4, such that the given cubic Newton map is in the boundary of H. So if H has a prefix Julia critical point, then there exists infinitely many type IE hyperbolic components, such that the given cubic Newton map is in the boundary of the type IE component. This is the key difference between the type IE component and the non-type IE component. Okay. Okay. So may I ask? So it's a talk for 1 hour or for 1 hour and 40 and 30 minutes. Okay. Okay. Great. Thank you. Yeah. Thank you. Okay. The next step is okay. To rule out the quartic limits, we use the classification of PCF Newton maps. So now let me first introduce the extended Newton graphs. So we already know the Newton graph, which is just the plane image, the union of the plane images of fixed internal rays. So then the extended Newton graph is the Newton graphs. It contains the Newton graphs and the Hubbard trace and some Newton trace. Okay, Hubbard trace is to deal with the renormalization part, and the Newton race is the race crossing the photon components and containing the Newton graphs and the Hubbard trace. Here is an example for the extended Newton graphs. So the gray segments, the gray edges are from Newton graph. The white edges are the Hubbard tree, and the yellow edges are the Newton rays. Okay. For any PCF Newton maps, we have the extended Newton graph. We have an extended Newton graph. So then the classification of the PCF Newton map gives the description of Newton maps by the set of abstract extended Newton graphs. So roughly the the abstract extended Newton graph is just a dynamical graphs. From the extended Newton graphs. So for we denote the G to be the set of abstract extended Newton graph modulo conjugates, modulo equivalence. The equivalence means for two abstract extended Newton graph, they are equivalent if the extension of these two map on the whole sphere are certain equivalence. Okay, so now there is a bijection between the set of PCF Newton maps modulo affine conjugacy and the set of abstract extended Newton graphs modulo equivalence. So such that for any given Newton abstract extended Newton graph, its pre-image has extended Newton graph equivalent to the given abstract extended Newton graph. Okay. So the last piece to use to rule out the quartic limits is the rigidity of PCF Newton maps. Okay. In fact, there's a more general. Okay. In fact, the rigidity holds for more general class of Newton maps, but here we only use the version for PCF Newton maps. So let's first introduce the combinatorial equivalence for two Newton maps. This means these two Newton maps are have same Newton graph and the same dynamics of correct points. So this roughly means the Newton graph two PCF Newton maps are combinatorially equivalent if they have the same Newton graph and the same dynamics on the Newton graph. Also, they have the same dynamics of the correct points. With respect to the combinatorial allocation. So, and we say two Newton map are renormalized in the same way. This means they have the same dynamics of renormalization with the same combinatorial positions to Newton graph. Then for two combinatorial equivalent PCF Newton maps, suppose either they are both non-renormalizable or they are renormalizable in the same way, then these two Newton map, these two combinatorially equivalent PCF Newton map are in fact affinely conjugate. Okay. So we will apply these three P's to rule out the quartic limits for non-type IE component. So how to do that? So let's consider the center of H and its extended Newton graph. Here H is a non-type IE component. So now we remove some internal rays in its extended Newton graph. This internal rays contains the one connecting K1 and some other internal rays in the root basin omega 0. After that, we get a connected graph containing post-collidical points. This is important, so we can do that because H is of type IE. So we can So then we apply the classification of the PCF Newton map and get a cubic Newton map whose extended graph is the graph given in step 1. Now we apply the Taylor-Serre result, so we get a hyperbolic component H prime in N4 such that the element G is contained in the boundary of H prime. Sorry, there's another typo. Such that the element G is in the boundary of H prime. Now we consider the center of H prime and applying the rigidity result to show the center of H prime is conjugated to the center of. Sorry, I should say okay. The center of H is conjugated to the center of H prime. Then in other words, we get the H prime and H is the same hyperbolic component in N4. So then we apply the connectivity. We conclude that the boundary, the partial infinity H is contained in AM3 bar. Okay, this is the way to rule out the quadratic limit for non-type IE component. So okay, then how to so okay, then for type IE component, so we cannot apply step 1 to we cannot apply step 1 to get a connected graph containing post-quadratic points because some quadratic points will some quadratic point is contained in K1. So if we remove the internal rays containing K1, connecting K1, so we cannot get connected. We cannot include some post-quadratic point in the resulting graph. So, but we observe that so if a quadratic point is maps into the omega 1 is the root emitted basin contained in K1. Then we can modify the argument about we can modify this argument and conclude that the partial infinity H is contained in N3 bar. Okay, so I mean, if otherwise, so if the quadratic point if a quadratic point when it first maps to K1 but not maps to omega 1, then okay, the degenerating is related to some phenomena called called the holes. Okay, so there's some bad degenerating happens. So it seems that the second case is in some. It seems that the second case cannot happen. So okay, so but we don't know how to root out the second case. So here we just guess okay, the boundary, the partial infinity H is contained in AM3 bar if H is of type IE. Okay, that's why we assume in case 2 the part we have the assumption the partial infinity H is contained in N3 bar. Okay, in fact, okay, the proof to rule out the quadratic limit, in case 1 is quite hard, quite difficult than the bounded result. Okay, so now let me give the proof for the result. So okay, if H is of non-type IE, then okay, the boundary and the infinity. We first show the boundary of infinity is contained in it contains a closure of hyperbolic component in N3 bar. This is just the deformation argument. So then we show the boundary and infinity is equal to the closure of a hyperbolic component in N3 bar. Okay, in this step we use perturbations and the rigidity result. So if H is of type IE, then we first show the K1 hyphen is converted to infinity except one special case. And in this special case, we show the quadratic point. The limit of quadratic point is a pole. This gives the proof for the boundary and infinity. Okay, now let's consider the boundary map. Okay, what is the boundary map? So let's denote this three set H to be the unbounded hyperbolic component in N4, such that the boundary and the infinity is contained in N3 bar. And we write H1 to be the set of closures of hyperbolic components in N3 bar. And let H2 to be the singletons in N3. So each point have a prefix Julia quadratic point. Okay, so then the previous result implies that there is a well-defined map from H to the union of H1 and H2, send hyperbolic components in H to the boundary and infinity. So we call this map the boundary map. Okay, so now we showed with Yang we prove this boundary map effect is a surjection. So if in particular for element in H1, then there is only finitely many hyperbolic components in H whose image is the given element in H1. But if for the element in H2, there is infinitely many pre-images. So this means given a closure of hyperbolic components in N3 bar, there is only finitely many unbounded hyperbolic components in N3 with whose boundary and infinity contained in N3 bar, such that the boundary and infinity is the given element in H1. Okay, if so for any given element in H2, which is a singleton in N3 with prefix Julia quadratic point, there are the infinitely many unbounded hyperbolic components in N3 whose boundary and infinity is the given singleton. Okay, the proof is just based on the surgery result for PCF unit maps and the previous result on the boundary and the infinities. Okay. Okay, I think that's all. Thank you. Thank you.
Alrighty. Okay. Welcome back to everyone to the Complex Dynamic Week. Now we are going to have the talk of Professor Jasmin Raissy, who got her PhD at the University of Pisa under the supervision of Professor Marco Abate. And now she's working as a professor at the University of Bordeaux. And today she's going to talk about a geometric approach to parabolic curves. Okay, welcome, Professor Jasmin Raissy. You can start whenever you're ready.
Thank you very much. Well, first of all, I would like to thank you all for being here connected. I would have loved to be in Peru and all together. Well, eventually we will get back to in-person conferences and meetings. So it's a very nice invitation in any case. And so let me also apologize because I couldn't come to the other talks and I will not be able to come to the other talks, but I saw that they are online. So I can watch the streaming there. Thank you very much. So today, what I'm going to tell you about is a joint work still in progress. Actually, we're going to several directions with Xavier Buff on parabolic curves. So the idea is that there will not be really a new theorem today. It will be just a new approach to all theorems by Hakim and Eckelt. So let me start from the very beginning, even if I saw that, so let me start from here. I saw that Liz gave a very nice talk and introduced a lot of the objects that I'm going to use today. So let me just start from the very beginning, just to set the setting. So the idea is that we want to study, so the goal is study the dynamics of, well, a tangent to the identity germ. So F from Cn 0 to itself, the germ of holomorphic map fixed in the origin. So F of 0 is 0 and tangent to the identity at the origin. So if I consider the linear part of my map at the origin, this is the identity. And so in here we have a fixed point and we want to know what happens to the orbits nearby. So of course, as any good question, one starts in dimension 1. And when you are in dimension 1, well, in here I put it very general, but you can think, so let's start with a baby example. Say K here is 1. So what do I have? If I have f of z, which is z minus az squared plus I order terms, but actually I don't care about the I order terms, and I simply have z, so I can factorize z, and I will have z times 1 minus az plus other stuff. And actually in here, I can change coordinates so that a is equal to -1. So let me, well, without loss of generality, I can assume a equals to, +1. And in here, so if we have f of z, which is z times 1 minus z plus I order terms, well, you see that I have, so in the complex plane, whenever z is real and positive, then this part here is going to be less than 1. And I'm multiplying my positive real point times something which is of modulus less than 1. And so on this part, on this real axis, on this part of the real axis, I will have somehow an attracting direction for the dynamics. And whenever in here z is real and negative, then 1 minus z is going to be bigger than 1 in modulus. And so I'm going to have a repelling direction. So of course, if I get back to my goal and I want to understand the dynamics in a small neighborhood of my fixed point, this is not a neighborhood, right? So because I'm just having two directions. But what it is true, our theorem, we can enlarge these pedals. So I'm going to have an attracting pedal here and a repelling pedal here, and they're going to intersect. And so I can say everything in a small neighborhood of the origin. And what I mean, so let me just have it a little larger. What do I mean by attracting pedal? So in here, if I take a point inside my attracting pedal, so in this riddle region around this positive real axis, well, when I iterate, I'm going to converge to the origin tangentially to this attracting direction. And well, if I try to say something similar it's not of the good size. Anyways, if I try to have it to see what happens for the repelling pedal, then I can't say that I'm going to infinity because my map is a germ. So it's defined only in a small neighborhood of the origin. But, well, a repelling pedal, so this red pedal here is going to be attracting for the inverse. So what's happening is that, okay, no. Anyways, so what's happening is that orbits are going to go out of this pedal infinitely many steps, and this pedal is attracting for the inverse. And well, you see here that, I managed. So you see here that one can generalize this picture. So I did it for k equal to 1. But if in here you have a tangent to the identity germ, which is not the identity, then, well, this means that you will have a first nonlinear term in here. And, well, you can do exactly the same stuff in here. So you can factorize it like, so this is going to be z times 1 minus a z to the power k plus other order terms. And you can define what this attracting direction will be and what the repelling direction will be. An attracting direction will be a direction so that a v to the power k is going to be real and positive, and it's going to be repelling if it is real and negative, because I put a minus in here. And so we have a complete description of the dynamics of the iterates of f in a small neighborhood of the origin. And you can ask, okay, so now I have this. This is local dynamics. Does it give any information about global dynamics? Is it interesting? I mean, of course, it's interesting. It's an interesting question, but is it going to be useful for other stuff, for example? And actually, well, the answer is yes. So, and essentially, everything is based on the fact that on each pedal, you can construct a coordinate conjugating your dynamics to the semi-conjugating the dynamics, to the translation by 1. So in here, if I go back to my little example, I had f of z, which was z minus z squared plus I order terms. Well, if I consider the coordinate u equal to 1 over capital U, then 1 over z, it's the end of the day here, so it says I wasn't paying attention. So what's going to happen is that it's conjugating the dynamics to the translation by 1, more or less. So it's going to go, well, u is going to go to u plus 1 plus well, a big O of 1 over u. So this is not exactly the coordinate that I wanted, but what it is true and one can prove is that in an attracting pedal, say this is my attracting pedal, you're going to be able to, well, to perturb this coordinates in here and to conjugate to the translation by 1. And why is this so important? Well, on one hand, this gives you a model for the dynamics. And on the other hand, it has been important in studying what's called parabolic implosion. So when you study parabolic implosion, well, essentially, you're going to link these two coordinates. Of course, I'm saying for two coordinates because what I'm saying is that I have a photo coordinate on every attracting pedal, but as I told you in here, a repelling pedal is going to be attracting for the inverse. And so I'm going to have a photo coordinate for the inverse on the repelling pedals, and I can go back and consider the parametrization, so the inverse somehow of my photo coordinate. And so, well, if I get back to my example, of course, I change my notation in here, so it's z plus z squared. So now I'm going to see what happens from a global point of view. And from a global point of view, I can consider all the iterates that are converging to the origin for my polynomial maps. And so it turns out that they are going to land in the parabolic attracting parabolic basin. And well, one can consider the Laverse map, which is simply this map. And for the moment, you don't understand. So it's linked to the dynamics, of course, but it doesn't have a dynamical meaning when you write it down. So what I'm considering is I'm taking an attracting photo coordinate, I'm translating by sigma, and I'm getting back with the repelling photo coordinates. Okay, so this is somehow telling to you how to change coordinates. And what it turns out to be true that this is related to the dynamics when you perturb your map. So you can consider the dynamics of your parabolic polynomial, and you can try to perturb it. When you perturb this polynomial, what's going to happen is that, so in here we had an attracting basin and a repelling basin. So let me draw like if they don't understand, intersect. And with this kind of perturbation, if epsilon is real and positive, what's going to happen is that my fixed point 0, so this has two fixed points, plus and minus is epsilon. And in here, what happens is that these two fixed points are slightly repelling. That is, if I consider the first derivative of f epsilon at plus and minus I epsilon, what I get is plus and minus twice I epsilon. And sorry, there is a one that I stayed in my pen. And so in here, what's happening is that, well, I have these two points which are fixed, which are slightly repelling. And well, the picture that I had in here is going to open, and well, I had an attracting, so this was my attracting pedal and this was my repelling pedal for this map. And here, well, orbits were going to the origin, and in here I was escaping, but this time when I take a point in here, well, it can go through this corridor because it gets slightly repelled by this point and slightly repelled by this point. And so one can ask, how can I describe this kind of situation? And it turns out that this is related to this Laver's map in here. We have epsilon n going to 0 and Tn, so the number of iterations, which is going to infinity and satisfies this condition, then, well, this perturb map iterated Tn times converts to this Laver's map. So even if at the first sight, this Laver's map has nothing to do with dynamics, it does indeed. And one can read the dynamics of this perturb map and the dynamics of the Laver's map. And so this is useful. This has proved useful in proving, for example, that near the boundary of the Mandelbrot set, the Julia set doesn't depend continuously on the parameter. And it has been used also by Shishikura to prove that the Hausdorff dimension of the boundary of the Mandelbrot set is 2. And it is also one of the key points in the proof of Bouffe and Cherita of the existence of quadratic polynomials with Julia set with strictly positive Lebesgue measure. So with all these important results in mind, one can ask, what can we say in higher dimension? Is it going to be, well, is parabolic dynamics going to be important to describe global behaviors also in higher dimension? And well, the answer is yes. So in dimension 1 plus 1 actually is 1 plus epsilon. I don't know why I put 1 plus 1 in here. So it's like what we proved in not so long ago with Oster, Bouffe, Dujardin, and Peters was that if the Laver's map for this map of phase 0 as an attracting fixed point, then this kind of map, which is called the skew product. So as you see, what I'm having here is that I'm combining the one-dimensional dynamics of the parabolic polynomial with a one-dimensional dynamics of another parabolic polynomial which has opposite attracting directions, but I perturbed it with this pi squared over 4, which goes back to Laver's theorem, times W, this W here. And so what we proved was that if the Laver's map for this map has an attracting fixed point, then this polynomial map in dimension 2 has a wandering for 2 components, which was something that stayed as an open question for time. And well, the idea is that to prove this, in here, we have this lemma ensuring that the Laver's map can have an attracting fixed point. So, and one of the key points in this proof was the existence, well, actually we didn't prove that, we just needed to have some sort of formal, the existence of a formal parabolic curve. So the idea is that I hope that I motivated you a bit on the fact that understanding the parabolic dynamics of a germ, the dynamics of a germ, of a tangent to identity germ at the origin, can give us information on global dynamics. And so with this in mind, let me go back to what happens in dimension 2. So in dimension 2, now I'm going back to local dynamics. I'm going to stay in local dynamics for the rest of my talk. And what do I have is, well, and I will stay in dimension 2, even if I could go also in higher dimension. So in dimension 2, I have a tangent to identity map, which is not the identity. So well, this time I can write, so I will have the linear term, which is the identity, plus I will use the homogeneous polynomials of a given degree to give, to write down as a sum of homogeneous polynomials. So this is degree 1 and this is degree k plus 1, as I did in one dimension. And again, my dream goal is to understand the dynamics of F in a full neighborhood of the origin. But, well, of course, there is a special case. If I have a one-dimensional curve passing to the origin, then, of course, F restricted to this one-dimensional invariant holomorphic curve is going to be one-dimensional, and I can use the Loufat-Mufrala theorem. But if I'm not in this special case, well, I can still ask, can I describe my my dynamics of this kind of maps? And the idea was that, so let me go back to my first slide. So in here, what we saw was that the dynamics was encoded. Of course, I have this tangential identity part, but all the information that I needed was encoded in this first nonlinear term. So the idea is that, well, maybe this first nonlinear term is going to give me all the information that I want. And so when one thinks about it, what we can say is that, okay, look, if I consider a vector field, well, a vector field given by this homogeneous polynomial of degree k plus 1, then I notice that this identity plus h, if I forget about this tail term here, is the Euler method of this vector field, defined of the vector field. So essentially, what I'm thinking of is that if I'm truncating the flow, the time one flow of the vector field defined by h at order k plus 1, so at this order, f is going to be more or less like this. And so, well, I have a flow, I have vector fields, I know a lot of things about vector fields, and what one can have in mind is that, oh, I can use the theory of foliations and what I know about continuous dynamics. But the point is that usually what we know about continuous dynamics generated by a vector field in C2 is about complex trajectories. And in here, what we are interested is in real trajectories, because when I iterate f, I'm iterated at real times, actually integer times. So, yes. So it is natural to ask whether if my vector field as real trajectories, is it the same for converging to the origin? Is it going to be the same for my German tangent identity? And the answer to these questions goes back to, so the first answer, sorry, to this question goes back to Akin's and Rical's results. And of course, you heard a little more, I think it was yesterday in this talk. And you could also ask, okay, what happens if my vector field admits periodic real trajectories? Well, does the germ of my tangential identity germ admit small cycles? And the answer is that we don't know yet. Of course, if I consider the flow of this vector field, then that it is easy to answer. But the question is, I take a vector field, well, this vector field psi generated by h. So it's an interesting question to ask whenever this has whenever this has periodic real trajectories, is it always true that a tangent to the identity germ starting at with exactly this homogeneous order K part is going to have small cycles? And the idea is that we don't know yet. So, okay, what we started to do with Xavier was, as I told you, motivated by what we did about wandering domains in dimension 2. And we wanted to understand better the results of Hakim and Eckhout's from a more geometric point of view. So let me just recall to you something that you heard yesterday in this talk. So, well, in here, I don't know, but I don't think she was working, I think, in higher dimension. So, but it's easier if you are in dimension 2, well, you have your homogeneous map of degree k plus 1, and it induces a rational function on the Riemann sphere of degree k plus 1 with k plus 2 fixed points. And the straight lines about these fixed points are complex trajectories that are called characteristic directions for my vector fields. They're going to correspond to the separatrices. And well, the idea is that the behavior of the sheet covering P1 minus the K plus 2 fixed points near a characteristic directions depends on the multiplier of H at the corresponding fixed point. And so one should be able to, for example, say whether you have an attracting basin considering this multiplier. And so in here, what we're going to search for are petals in high dimension. So of course, when you try to understand, so let me go back, where is it? Yes, when you try to understand this kind of map, you still have in mind the dynamics, what you know about the dynamics in dimension 1, and it is natural to ask, is it true that in dimension 2, can I have a low-Fatu-Flower theorem? And if you ask such a question, then it is normal to try to understand in which sense, because, well, you want to understand what kind of petals you can have. Are you going to have two-dimensional petals or one-dimensional petals? And if I go in higher dimension, well, three-dimensional petals, so open domains or curves. And so, well, the first thing one can look at is trying to find curves of points where I converge to the origin. So somehow parabolic petals that are usually called parabolic curves. And so if I go back, so in here, what I told you was that I had this k plus 2 fixed points for the rational function induced by H, but one can simply say, okay, look, I'm going to see whether I have a vector which is non-zero so that my homogeneous polynomial is equal to a multiple of this vector. And actually in here, I will need a more specific definition. I will call the characteristic vector a complex vector, which is non-zero, and so that the homogeneous polynomial part, first, well, h of b is equal to minus b over k. And the key observation of Hakim is that if an orbit converges to the origin tangentially to a non-zero complex direction, then either this direction is going to be degenerate. So in here, I'm going to have h of v is 0. So in this case, v is called degenerate, a degenerate characteristic direction. Or or it is a characteristic direction. Sorry. So actually the characteristic vector is a vector such that, so remember that my f, sorry, I put it an x because I was in dimension 2. H plus h of x plus I order terms. And this is a homogeneous polynomial of degree, k plus 1. And f is sending, well, in here I'm sending cp 0 to itself with p at least 2. So I'm simply saying that I take a vector such that, well, when I apply my homogeneous polynomial to this vector, I recover minus b over k. Is it clearer? Thank you. And so this is the definition that we gave with Xavier, because we needed to have a good representative, well, with this sort of behavior. But the idea is that Hakim observed that if you have an orbit converging to the origin and ref tangentially to a non-zero complex direction, then either this direction is degenerate, meaning that h of v is 0, or h of v is equal to lambda v for some lambda, which is non-zero. And what I'm simply saying, and so in this case, it is called a characteristic direction, a non-degenerate characteristic direction. And well, once you have such a direction, you can choose a representative, which is a vector, a characteristic vector, so which is doing what I want here. And well, what Hakim proves, she proved it in 1998. So this was a statement given by Ekau maybe 10 years before, but he proved it with some techniques which are not analytic. And what Hakim did, she proved it with analytic techniques. So the idea is that if you have a characteristic vector, so if you have non-degenerate characteristic directions, then you have at least k invariant one-dimensional pedals. And so usually called k parabolic curves because they are one-dimensional. And for every point in this pedal, you have this behavior. So the iterates of points are going to converge to the origin like v over n to the power 1 over k, which is exactly what we have in dimension 1. And moreover, you can associate to this characteristic vector a similarity class of a matrix. I'm not going to enter into this today, but if this matrix has d eigenvalues with strictly positive real parts, then you have at least k petals of dimension d plus 1, which are tangent to the right space, meaning cv plus e at 0, where e is the sum of the corresponding eigenspaces. And there exists, so, and actually one important part is that there exists a photo coordinate conjugating the restriction of f to the petal to the translation by 1. So we have this, we have what we had in dimension 1. So of course you can ask what happens when v is a characteristic direction, but it is not non-degenerate. So yes, and actually if you ask such a question, then you have to see, well, to check about further results. So essentially you have to check about the results proved by Abate and Tavena, by Luis Vives, by Rang, by Lapan, by Molino, by Lopez-San, and etc. and etc. and etc. And so I think the newest results are due to, well, Lopez, Riban, Sanz, and Luis Vives, and she talked about it yesterday. And in dimension 2, what it is, well, for my taste, the most exciting result on this topic is due to Lopez and Rosas 3 years ago. So what they proved is that whenever you have a characteristic direction, there is always a parabolic curve centered at D. So there is always a one-dimensional pedal where you have that orbits converge to the origin tangentially to my characteristic direction. So if the characteristic direction is non-degenerate, this is due to Akim. And what they proved is that even if it is degenerate, then, well, they can prove the existence of a parabolic curve. So there is one good thing about all these results is that, well, they improved Akim's result, but and I'm putting myself into the picture. So the point is that all these results are following more or less the same path. So to prove, yeah, there is a warning that I always forget about it. There are examples of maps with orbits converging to the origin without being tangent to any direction. Actually, we are working on this with Xavier to understand and describe better these kind of examples. So, but what I was saying is that the strategy of all these results, more or less, follows the same strategy as Akim does. So if you read Akim's paper, you will have to have clever changes of coordinates to put yourself in the good position to be able to use a fixed point theorem. So you're going to change coordinates, so change your setting in a clever way, and to reduce yourself to work with a Banach space of holomorphic graphs, where you can define a closed set with some good analytic estimates, and then you find a contracting operator. And then you have a fixed point because you have a contracting operator of a closed set and you have a fixed point. Well, what our strategy is to replace these two steps. So we replace the first step by some sort of 1 plus epsilon blow up. I'm not sure that I will have time to enter into these details. And we replace this Banach space of holomorphic graphs by a key proposition on contractions of graphs. So I think I have time to enter at least give you the statement of this key proposition. And to get to the key proposition, let me start by a proposition which is classical. So this is, let me point it out. So this is very classical. So this is not difficult. So, and maybe it's easier if I give you if I do it with a picture. So the statement is quite, quite precise because it's a statement, of course. But so what I'm saying is that we take the product of two bounded convex open sets in CR, one in CR and one in CS. So let me take my product, U and V in here. And then of course I need some, so if I want to be very precise, I have to have a holomorphic isomorphism from a neighborhood of this product to another neighborhood of this product within inverse G. And what I'm asking here is that if I consider the projection, so if what I'm saying is that I'm going to contract in the vertical direction by F. Okay, so the image of U times V under F, when I project it on and U is strictly contained in U. So I have contraction in this horizontal part by F. And let me use this. And if I consider the inverse, well, what's going to happen is that I'm going to contract in the vertical direction. And more or less, moreover, whenever I consider the image of the vertical segment in here, it's going to be something which is more or less vertical, and it contains the closure of V. And whenever I do it with the inverse, so if I've taken a horizontal segment, it's going to be sent by G, and something a little bigger containing, so its image will contain the closure of U. And so whenever I am in this kind of situation, then there exists a map phi from U to V, and there exists a unique psi from V to U, holomorphic, with relatively compact images, such that the image of, the graph of phi is F invariant, and the graph of psi is G invariant. And well, as you see, I call this graph X because it's horizontal, it's vertical, and the other one is going to be horizontal. And the two intersect at a saddle fixed point for F with stable manifold X phi and unstable manifold X psi. So this is very classical because, well, and essentially what we're saying is that whenever I am in a situation where I have a saddle fixed point for F, I will be able to prove to apply this kind of proposition because I will be in this kind of setting. But the point is that I don't have a saddle fixed point. I have a fixed point which is tangent to the identity. Well, and this is why we have to perturb, so I wrote down just a little the proof of such a result. So to prove such a result, well, you endow the space of horizontal and vertical compact graphs with a metric. And to do that, you use the Kobayashi matrix on U and V. And then, well, the graphs transformation induced by F and G are contracting on vertical and respectively horizontal graphs. And what I was saying is that, well, in our situation, one has to perturb this situation. And the idea is that, so we start with the same setting. So let me maybe do it a little bigger. So I have the same starting setting, but this time what's happening is that when I apply F, this sort of square is going to go to something like this. This is under F. And if I consider the image under G is going to be, well, there is going to be something which is not going to be contracted, but I'm going to have this sort of image. And again, if I consider the image of a vertical segment, I'm going to go to a somehow vertical graph. And in here, if I'm considering the image of an horizontal segment, I'm going to get to this sort of kind of horizontal graph. But so this is the initial part. And so since I relaxed my hypothesis, now I'm still able to find phi and psi holomorphic maps with relatively compact images such that the graph of phi is F invariant and the graph of psi is G invariant. But what I lose is the uniqueness in here. But this is going to be enough. Sorry, I think, yes. And actually the idea to prove such a result is really easy because you just perturb the hypothesis this situation to an hyperbolic situation. And then we pass to the limit because the holomorphic maps from U to V bar and the holomorphic map from V to U bar are compact in the local uniform convergence topology. So once we have this, sorry, yes, I think I have it here. So once we have this proposition in hand, plus the epsilon, one epsilon blow up that I will not have time to talk about, sorry about that. So to finish, what we do is the following. So now to finish, we get, so let B be a neighborhood of the origin and define, sorry, X is the points in V such that there exists epsilon positive so that Xn, which is simply the iterator under F of X, is equals to V over N to the power 1 over K plus with the law of N to the power 1 plus epsilon over K. And the claim is the following. Yes. So there exists epsilon naught positive such that X is equal to X epsilon naught, which is simply, well, let me write it again. So I'm taking the point in this small neighborhood such that Xn goes to the origin like, well, along V, like 1 over square, sorry, kth root of N plus with the law of N to 1 over N to the power 1 plus epsilon naught over K. And this is a D plus 1 dimensional parabolic manifold. Where D is, so let me just go back to what I'm proving. So what I'm proving is, yes, it's going to get back here. So I'm having this, I'm proving this part in here. Up, sorry. Takes forever to get to the point. Yes. And the idea is, and to prove this, we use, so to prove the claim, we use the key proposition, of course. And I think my time is essentially over because I also have a meeting at 5. And if I want to leave some space for questions, I have to stop here. So let me thank you very much for your attention. Thank you very much. Hope to see you in person someday soon. So let me stop sharing maybe. Yep. Thank you very much. Yeah, sure. I can send it to you if you want. And well, sorry, I gotta go. So bye.
Okay. Okay, entonces... Ok, entonces... ¿ya está grabando? Ok, okay. Continuando con el minicurso, bueno, de hecho es la parte el último episodio del minicurso. Eso el pase al profesor Alfredo Poirier. Okay.
Well, hello again. Today we're going to not finish, right? Because actually this is an open field, and with me, you're just seeing the surface. We're touching the surface. Remember that first day, we start with an example of what we can learn about the iteration of squaring, especially what's squaring in the circle. And we derive a lot of properties. Those properties, in some sense, were easy because they can be derived either by common sense or, if you have some experience in dynamical systems, by actually, I would say, cylinder coordinates, Markov partitions, and a lot of techniques, right? For example, the periodicity of or the density of periodic points, the existence of points with dense orbits, and so on. Then we took off with some iteration of polynomials, and we derive also some properties, sort of property. We argue, defending that some properties are going to be true. And it was not until yesterday that we learned that there was a simpler way to express most of the properties of what we have learned about iteration of polynomials, right? And as a byproduct, and introducing new techniques, we learned something perhaps new about the understanding of Newton's method. Now, today is the turn to try to extend most of the properties that we have learned from the circle, and there was no surprise, right? To arbitrary polynomials, or more generally, to arbitrary Julia sets. So the idea, arbitrary rational functions. The idea is that we're going to derive some properties with all the apparatus that we have mounted. It will be the one that relates normal families. And we're going to derive, remember, the normal family arguments involves the Fatou sets, but actually there's also implications for the Julia sets, for the sets of non-normality. And learning something about the Julia set, we will learn again something more about the Fatou set, and so on. No, that's the idea. So, but again, we're going to see several interesting proofs. Those are incredible that those proofs are nowadays, we will say, without afraid of being wrong, that they are like 100 years old, right? And it's incredible that several of those proofs actually were devised long before actually the idea of computing was a common feature of everybody. Okay, so the Julia set, remember, is a place where our dynamical system is not normal, right? Normal, in that case, means convergent, right? So Julia set means that we are far from convergent. We are far for actually a uniform way to understand things. So that's the time is now to see if we can find some regularity inside the Julia set. Okay, our first feature is going to involve the concept of exceptional sets. Something that people who does studies complex analysis has learned, that the way to count in complex analysis is 0, 1, 2, infinite. Okay? By 0, we mean actually elliptic. Perhaps by 1, we mean actually, by 1 or 2 we mean parabolic, and for more than 2 is where what that turns us into the hyperbolic way. So the idea now is actually that we're going to count. And as in any dynamical system, the most basic individual constituent of a dynamical system for us is a grand orbit, right? You can go from here to here, and you can go from several places to here. And that's the idea that comes from dynamical systems. So if you think that you can play with time, you can go forward in time by iteration, and you can start looking for pre-images and to start looking where are you coming from. Okay, so that's the idea. And remember, we are in a rational function. You can even imagine that you are working with a polynomial. It makes not a big difference. But the idea is that whenever you're trying to solve an equation, right? If you want, or you have a rational function, and remember our basic assumption is that we are in a degree more than 2. If you want to come here, you're trying to solve your equation f of z equals to that point. And that represents an algebraic equation. And that algebraic equation, being our rational function of degree bigger than 2, will have, say, 2 solutions counted with multiplicity. So, except if you are in with a critical point, there are precisely, in a degree d rational function, d ways to hit a point in an immediate step. But if you look to the past of those, each of those will have in turn d pre-images. Of course, things can happen, right? Because here the magic word is that we have learned during the years is the magic word here is with multiplicity. So we're trying to see how the multiplicity in that big tree, which is especially a backwards, well, it's also you go forward and you go forward as many steps as you wish, and then you go backwards. It will be denoted tree at each point, at each vertex. In general, that will be infinite. The magic word here again is in general, right? Essentially, or counting multiplicity. So the idea now is, let's see, counting exceptions, how small can be a grand orbit. Remember, in general, it's going to be infinite. So whenever we have a degree 2 or more rational map, a set will be exceptional if it is finite and totally invariant. So that means if you look for your destiny ahead of you, there is only a finite set that you will touch. Therefore, you are either a periodic point or a pre-periodic point, right? Because sooner or later you are going to, because the orbits in general are infinite, and you are only allowed to work in a finite set, numbers are going to repeat. And when it starts repeating, they will repeat forever. But not only that, right? You also want to see what happens with the pre-image of each and every point, right? So, being an exceptional set, a finite and totally invariant set, well, remember, a totally invariant set is a union, perhaps even a disjoint union of totally invariant sets of grand orbits, right? It's pointwise. Therefore, you will have that set will be exceptional if and only if it is a finite unit of finite grand orbits. There are several examples. The easiest example, the easiest place to find an example is at the point of it at infinity of a polynomial, right? Whenever you have a polynomial, you're working in the extended complex numbers. Whenever you're playing with the complex numbers and you iterate, you reach another complex number. If you look for the past of a complex number, the past of the complex number is a complex number. Therefore, infinite, if you map infinity, the answer is infinity. And if you ask which are the points from which you will reach infinity? You will only get infinity. Therefore, with infinity, you have that infinity is itself a grand orbit, and because it's finite, it is an exceptional set. Another friend of us is not only infinity, but for polynomials, you have that if you iterate c to a power, remember we are actually only allowing ourselves to work in degree bigger than 2 rational functions, so in this particular case the degree will be bigger than 2, you will have that 0 is also a total invariant set, because from 0 you go nowhere, and the only place where you can extract this root of 0 is 0. Now, those are exceptional sets, both which are grand orbits with a single element. There is another grand orbit, finite grand orbit, but in this case that have exactly 2 points, right? Is the inversion of the c to the d, right? Because here you have that 0 and infinity are the only critical points. So therefore are actually full critical points, if you can call it that. And the image of 0 is infinity. So the only way to reach infinity is via 0. And on the other hand, if you replace infinity, you will get 0. And infinity is a critical point, and the only way that you can get 0 is with infinity. Therefore, that's a completely invariant set, and that's that exceptional set has 2 orbits. Okay, let's consider the polynomial case, right? In the polynomial case, you will have that any finite grand orbit, of course, here you're talking about a degree at least 2. In a degree 1, for example, if you have a rotation, right? Rotation by 90 degrees, you will have that several orbits, full orbits has 4 elements, right? That's another reason to avoid that kind of exceptions and working with degree at least 2. But whenever you're working with degree at least 2, you have that any polynomial finite grand orbit will be a singlet. Of course, infinity is an example of that. But however, if you have another grand orbit besides infinity, well, it can only be if you, with a suitable coordinate, you are talking about c to the d. And therefore, in that particular case, you will have that only 2 elements will have. Okay, so let's see why. Why is that true? Let's take n elements which are different. And I am not going to iterate them. I'm going to look for its past. And the question is, remember we are in a degree d, and the question is, in how many ways we can reach this point? Oh, the magic way is, it will be d ways counting with multiplicity. So, I claim that the preimage of the set, or that means the only way that you can reach those points are physically. I'm not counting with multiplicity. I just tell you, counting multiplicity is nd. So I am now going to count physically. Well, that's sort of easy, right? Because now there are d minus 1 critical points. We're in a polynomial. A degree d polynomial, we take derivatives, that's a degree d minus 1 polynomial. The critical points are the zeros. And the only places that will have multiplicity are precisely the critical points. Therefore, if I want to bother you making all of those values critical values, the most that I can miss are d minus 1 extra elements. So in total, you will have nd counting with multiplicity. I will give you for free the multiplicity, so I take it away. So I will have nd minus d plus 1 different values. Okay? So let's see. What happened with n is bigger than 1? if n is bigger than 1, look at this value. This value will be bigger necessarily than n. Right? Because d is bigger than 1, right? So here you want to solve, put it this way, you want this, you want to know when this is bigger than 1, or when this is bigger than n. And if you want to solve this inequality, you bring this to the side, and you will have n d minus 1. Write it this way. I'll have it. If I bring n to the other side, I will have dn minus n minus d plus 1, which is precisely n minus 1 times d minus 1. And when this quantity is bigger than 0, this quantity is bigger than 0 if and only if both quantities are bigger than 0. Of course, with that degree, no problem. D is bigger than 1 because D is bigger or equal than 0. So this quantity is bigger than 1, and this quantity will be bigger than 0 if and only if n is bigger than 1. So when n is bigger than 1, the size of the successive images will keep growing. Therefore, what is the only way that you can construct invariant finite sets is with one element. And not only that, because grand orbits are necessarily singletons, but you cannot have two grand orbits here. Because if you have two finite grand orbits, the preimage of this will be of 2, the preimage will be bigger than 2. Therefore, one of those is missing some elements and cannot be say, a grand orbit. Okay, this works for polynomials. What happens now with a rational function? Okay, the idea with a rational function, this is an exercise, the proof is exactly the same, is that the exceptional set of a rational function consists of 1 or 2 points. If your grand orbit is a singleton, well, from now on you declare that that point is infinity and you're in a polynomial case. So then that rational function is conjugated to a polynomial. So the other thing that might happen according to this is to have a grand orbit to have 2 points. Then what you do? You set one of the exceptional points at 0, the other exceptional point at infinity, and you get that this is precisely your frame. Okay? So what's the proof? The proof is exactly as in the polynomial case. Only that now counting with multiplicity means a little bit different thing, because a rational function of degree d has 2d minus 2 critical points. Therefore, then you have to correct yourself, right? At least that kind of terms, and then you should analyze separately the case n equals to 1, n equals to 2, and what happens with n bigger than 3. However, there is a consequence of being in the polynomial, well, not in both cases, right? Because we have seen that exceptional sets cannot have 3 points, right? And we will have that if a point does not belong to an exceptional set, then there are at least 3 different ways to reach that point, right? So if you want to come here, there are 1 point, another point, another point. So this can map to this can map directly to this. If not, it will map here. It's not exactly a corollary of the statement, by the way. It's a corollary of the method of proof. Okay, and this is important because remember, the number 3 is the magical number when we're working with normal families. Remember, the idea is that if we are going to want something to be a normal family, we must be looking for things to avoid at least 3 points. And here, the idea is that, well, perhaps if we avoid these 3 points, we are avoiding in the future this one or whatever it will be. Okay? So, look at the exceptional sets, right? At the end, we have constructed or we have realized that in the polynomial case, infinity is an exceptional set. And remember, in the polynomial case, infinity, in the degree at least 2, is a super attractor. And super attractors belong necessarily to the Fatou set. What else do we know? Well, the other possible case is C goes C to the D, and consider the origin. Well, in that case, the origin, right, is also a critical point, a fixed critical point, therefore is a super attractor. Right? And that belongs to the Fatou set. And the third possible case is when you have set goes to 1 over C to the D. In that case, you will have a critical orbit that goes from 0 to infinity, but critical periodic orbits are necessarily part of the Fatou set, right? So therefore, exceptional sets are always in the Fatou set. Okay, so our first conclusion. Remember our first day, and I asked you to imagine neighborhoods very close to the unit circle. The unit circle in that case was the Julia set, as trapezoidal neighborhoods. The idea for you to imagine those as trapezoidal neighborhoods is that you can predict how it grows. And once you understand how it grows, you understand that that neighborhood swallows everything. Sooner or later, every point, perhaps with the exception of 0 and infinity, is going to be in the image of that trapezoidal neighborhood. Well, for general polynomials, not only for polynomials, even for rational functions, the same is true. So in this particular case, suppose that you have an open set that intersects the Julia set. Then the union of iterates of that one misses at most 2 points in the Riemann sphere. That is exactly what happened with the circle, right? Well, we have extra information. The omitted points necessarily belong to an exceptional set which does not intersect you. And the proof is sort of easy, right? You're in the Julia set, right? What happens with the restrictions of the iterations to this set? The restrictions of the iterations to that set cannot form a normal family. And the magic word that cannot form a normal family means what? Means that misses 2 points. And that is precisely what I am claiming. If it misses more than 2 points, I can apply Montel theorem, and this neighborhood will belong to the Fatou set. And if this neighborhood belongs to the Fatou set, it will never intersect the Julia set. Okay, so there is a corollary, right? Because this union misses at most 2 points in the Riemann sphere. And it says that the omitted point belongs to an exceptional set. Well, the exceptional set as I told you before, belongs to the Fatou set. Therefore, the full Julia set is included here. If the full Julia set is included here, and the full Julia set, remember, is a compact set. So this is a covering of a compact set. Therefore, there is a finite subcover. If there is a finite subcover, well, we can take all consecutive elements until we are sure that we have covered the Julia set. And therefore, we will have that if you get an open set that hits, that intersects the Julia set, then there is some point in which the Julia set is included in the union of all of them. Look, here you don't need to know exactly what was the shape, right? And here, instead of picturing the proof with trapezoidal neighborhoods, what we are doing is we're picturing the proof with Montel's theorem. If we don't hit all except 2, Montel applies. And if Montel applies, that's normal. And if it's normal, it's not a Julia point. And how about our next favorite property? Well, the preimages of a points are dense, right? Because what means that a preimage is dense? That whenever I have an open set, right, I will find a preimage there. Well, how you find a preimage of any point in the Julia set? Very easily, right? You iterate until it swallows everything. If it swallows everything, the point that you are looking must be in one of the images. If it's one of the images, well, you know what that means, right? That there is a point in U such that you get it here. Okay? So the preimages of any point are dense because they intersect, the preimages intersect any open set. Of course, from here, we can start again a bear type argument and see if preimages are denses, right? And the set of points that hits an open set is open because of continuity. Well, if you have open and dense, you will have by intersection of all possible neighborhoods, you will have a point or you will have a dense set such that its iterations will hit any open set. That means that, that its orbit is necessarily a dense set. Okay. Continue. There is this property I'm not going to prove, right? That is important, that the Julia set has no isolated points. That's a very easy proof. However, the ideas involved are a little bit different, but it's worth it to write it down. And what is important here is that this is the beginning of a comparison between the Julia set and the Fatou set. So the question is which is smaller, which is bigger. In principle, the Fatou set is much more easier to understand, right? Because there's chaos in the Julia set. So the question is, do chaos always exist or does normality always exist? The truth is that the dark force wins always because the Julia set is the one that actually is bigger. And look at this argument. Suppose that you are in the polynomial case, right? And suppose that you, inside the Julia set, you find a whole neighborhood of Julia set points. That's not possible. Because remember, the Julia set is bounded. And if you have that a Julia set is surrounded by a neighborhood, if the Julia set is surrounded by a neighborhood of also Julia set points, the iterate is going to be bounded. But remember, if you have a set of iterations which are bounded, again, you can apply Montel theorem, and necessarily you will have that applying Montel theorem, you will have a normal family. But if you can apply a normal family, then necessarily you will have that you are not in the Julia set as you are in the Fatou set. Okay? However, the same argument I'm just telling you that for the polynomial case, that's for the polynomial case, that might not be true, that they would not have interior, but there are examples of rational functions. If I have time, I will hint you an idea of how to construct a rational function, all of which points in the Riemann sphere are or in the Julia set. Right? And the idea is that you have this argument. Suppose that you have a rational function for which the Julia set has interior points. Well, if you have a rational function with a Julia set which has interior points, you have a non-empty set in the interior of the Julia set. And here you apply two properties. The first property is that the Julia set is invariant. So therefore, the image of all of those points belongs to the Julia set. On the other hand, what happens whenever you have an open set that intersects the Julia set? You will have that sooner or later it will cover the Julia set, right? Not only that, you will have that any open set that intersects the Julia set, the union of the images will misses at most 2 points. So what happens? Therefore, the Julia set, being invariant, misses at most 2 points, but the Julia set is closed. Therefore, if you take away 2 points from the Riemann sphere, you necessarily, if you take the closure, you get the full Riemann sphere. Right? So therefore, this is a kind of nice argument. And in fact, there are rational functions whose Julia set is the Riemann sphere in full. So the question now is, how small can the Julia set be? And if you allow me something which is very easy to believe, however, it will take a couple of pages to prove, I will prove you that the Julia set of any rational function of degree at least 2 is at least contains a point. Okay? Well, if it contains a point, it contains a grand orbit. As it contains a grand orbit, right? And we know that exceptional grand orbits belongs to the Fatou set, it will contain a non-exceptional grand orbit. However, what happened with non-exceptional grand orbits? They are infinite. So therefore, once you detect 1 point in the Julia set, there are an infinite number of points in the Julia set. And the argument is like this. We're in a rational function, right? We're a rational function. Every rational function has a fixed point. It's a rational function. You said your rational function equals to a point, and that will have d solutions, counting with multiplicity. So it will have at least one solution. Okay. But there are equations which has only one solution. Square, for example, right? x minus 1 squared equals to 0 has only one solution. And there are fixed points, or there are quadratic polynomials with one fixed point. However, the idea is that what must happen is that it contains at least 2 periodic points. So if you accept that, which is not very difficult to prove, right? But actually, it's not the place to prove it here. If you accept that a rational function contains or has at least 2 periodic points, different periodic points, right? I don't know if you can imagine a rational function where there does not happen. But you write it down and you will have actually, in most cases, you will have 2 fixed points, right? Well, what happens if there is only one fixed point? Well, if there is only one fixed point, it's sort of a theorem, you will have a period to necessarily a period to orbit, different. Right? Therefore, you will have at least 2 periodic points. Now, I'm trying to prove you that the Julia set of this rational function, which has at least 2 periodic points, is non-empty. But remember that the Julia set of a rational function and the Julia set of any of its iteration is exactly the same as a set. I'm trying to prove it's not empty. So if it's not empty for this, it's not empty for this. So I can assume that I have just turned those 2 periodic points, I just convert them into fixed points. So I have my point A, my point B. Okay? Okay. Now, neither of those 2 points can be exceptional. Really, well, they can be. But suppose that one of those 2 points is exceptional. If one of those 2 points is exceptional, we are either in a polynomial. In a polynomial has Julia sets. Or we are actually in the iteration of set goes to 1 over set to the d, whose Julia set is a circle, and therefore it has Julia set. And that is exactly what we were trying to prove. We're trying not to complicate ourselves. We're trying to prove that all rational functions do have a Julia set. So if we have a Julia set, if we have a rational function that allows exceptional points, we do in fact have Julia sets, and we won, and we forget about this issue. So suppose that we are with a Julia set with no exceptional points. Well, those are fixed, they are not exceptional, and therefore there are a lot of ways to reach those points, right? Like a tree. How can I reach this? It has at least one preimage, those will have a preimage, and there are a lot of ways to hit this point. In fact, I can call this is the dead end of all the grand orbits, right? And this is the dead end of all of this grand orbit. And both grand orbits are necessarily infinite sets. Okay? Okay. We take those points, A and B, and we consider the set of all points that will reach that end. So that will, at the end, I'm only telling you that I am considering the grand orbit of A and the grand orbit of B. And those sets are infinite and they are disjoint because either you finish in A or either you finish in B. Now, suppose and this is completely absurd, right? That the Julia set is empty. Well, if the Julia set is empty, the complement is the normality set. And if it's empty and we are working in the Riemann sphere, we will have that the iterations form a normal family in the whole Riemann sphere. So let's see. Well, there is a subsequence so that the iterates will converge to a function which is defined in all the complex numbers. But we have extra information, right? Because if you evaluate in the grand orbit of A, eventually you are hitting A. And once you hit A, the further next iterates will be A. Therefore, phi evaluated in any point here gives you A. But this is an infinite set in the Riemann sphere. And if in the Riemann sphere you have an infinite number of solutions of an equation, you will have that actually everybody takes value A, right? Phi is constantly equal to A. But remember that we have two fixed points. So therefore, the friends of B can say exactly the same. And therefore, what will happen? We will happen that this has actually two limits. It has limit A, it has limit B. That's impossible, right? Because both are convergent, and if it's convergent, it can only converge to one of them. As a consequence, what happened? As a consequence, we get that normality is never granted in all the Riemann sphere at the same time. Well, if the Julia set contains at least one point, it contains a full grand orbit, a full non-exceptional grand orbit, therefore it contains an infinite set. But what happens with open subsets of the Riemann sphere? Open subsets of the Riemann sphere that misses 3 points are hyperbolic spaces. They are uniformized by the unit disk. Therefore, they are hyperbolic spaces. So one of the first consequences of the theory of what we have learned is that whatever you do, you will have that the Fatou components will always be an hyperbolic space. And once you work with hyperbolic spaces, you know that lots of nice things are going to happen because you have available, for example, Fatou's Schwarz lemma, for example, right? And as a corollary, you will have that in each Fatou component, you have at most one periodic point, right? And in particular, we'll have that when you have an invariant component, a forward invariant component, if it contains a periodic point, it is necessarily a fixed point because you can escape from that component. Okay? And the idea of the proof is very simple. You can replace f by f to the n, and you can assume that this component is invariant and that the periodic points are fixed points, right? But in an hyperbolic space, a function which has more than one fixed point is necessarily periodic. But that's wrong, right? Because in that component, our function will be periodic, right? It will be locally, it will satisfy, in an open set, it will satisfy this. But if it satisfies this condition in an open set, it will satisfy it globally. And therefore, that cannot happen, right? Because the only rational functions which are periodic are functions that has degree 1. That will happen only in that particular case. Okay? This is actually a review of, I have already given you the proof if I'm not wrong, but let's put it in place about the transitivity. Right? The idea of going from one place to the other, right? And we have argued this before, and suppose that you will have an open set that intersects the Julia set, and then for any open set, which intersects the Julia set or not, we will have that sooner or later they will intersect, right? Because otherwise, if you avoid hitting an open set, you're avoiding hitting an infinite number of points. If you're avoiding more than 3, you belong to the Fatou set, right? So that would be that. Otherwise, you are in the wrong place. Okay, I have told you about this, right? Is that there are points in the Julia set with dense forward orbit. In fact, you will have that a dense set of points do have dense forward orbit. Okay, and the proof is exactly the same. You will have that the set of points that hits an open set is dense and open. And therefore, the set of points that hits every open set is the intersection of all of those. Therefore, being us working in a bare space, in a second countable compact metric space, we'll have that necessarily bare theorems applies in this part. Okay. Now, I just stating this, and the idea is that the most orbits are necessarily repelling. So I'm just going to tell you this for polynomials, right? It's also true for rational functions. And the idea is that whenever you have a polynomial of degree greater or equal than 2, there are at most a finite number of periodic orbits whose multiplier is a norm less than or equal than 1. Right? And in fact, the number of such orbit is never more than d minus 1. Of course, the idea is that there are an infinite number of periodic orbits, but only a finite number of orbits which are either attractive or neutral. In the rational function case, the bound here is 2d minus 2. It won't change, it will be a little bit bigger. However, that's finite anyway. There is very easy to prove that this is less than, if I'm not wrong, 6 times d minus 1. Right? In my book, I think I have a proof that the total number here is less than 6d minus d, which is important because what follows, we will need the fact that most of the orbits are repelled. Okay, in the case of rational functions, this bound is not d minus 1, but is 2d minus 2. As a consequence, we have that the periodic points, except a finite number of finite orbits, that means a finite number of periodic points, they are necessarily repelling. Okay? So, this is perhaps one of the most spectacular theorems in the theory at this level. It's a way that how can we manage to prove in this particular case that the periodic points are dense in the Julia set. Okay, so I want to prove that in the Julia set, points in the Julia set, periodic points are dense. Therefore, I pick an open set that intersects the Julia set, and the idea is that I am going to find inside a periodic point. Okay? So, draw your Julia set draw your open set that intersects the Julia set. And as the intersection of that open set and the Julia set is not empty, I have just found a point that belongs both to the neighborhood and to the Julia set. Okay? So start picking a point that belongs to belongs to both the open set that you want to work and the Julias. Okay, the idea is that we're going to find a periodic point in this neighborhood. Of course, if let's see, what I'm going to do is I'm going to find a repelling periodic point in that neighborhood. So if I don't want to find a neutral or an attractive periodic point, what I will do is ask. Inside here, and for sure it's not this point, because remember, in periodic points are finite. Right? And sorry, the number of those critical, attracting or neutral periodic orbits are finite. So if I found any of those inside here, I just leave them, I delete them. And if I delete a finite number of points, I am still left with an open set. Okay, if the point that I have found in the intersection is a fixed point, there's nothing to do. That is a fixed point, a periodic point in the Julia set. And what happens if it is not repelling? It doesn't matter. I never claimed that I was going to find a repelling point, right? I'm just going to find, actually, I was just going to find in every open set a Julia set element which is periodic. Well, this is a Julia set element. This is inside the open set. And if it's fixed, it is periodic. And there's nothing to do. Otherwise, it has a pre-image, right? It has at least one, if it is not a fixed point, right? It has a pre-image, right? Because if this one equals to this, the image of this is this, means that this is a fixed point. Therefore, here I have found a pre-image elsewhere. On the draw, here is your C naught. At some other place, you find this element here. If needed, right, we're thinking of U as a neighborhood of this point, and remember, we're going to find a periodic point inside here. So if we shorten this neighborhood and we find a periodic point, well, that periodic point in the shortened neighborhood is still in the original neighborhood. So nothing happened. So as I have that this and this point are different, I can shorten the neighborhood in such a way that the pre-image is also an open set, so that those two are disjoint. Okay? What else do I need? For technical reasons, if I am in the polynomial case, I can simply take this as an open set in the complex plane. And if this is an open set in the complex plane, not this point nor its image is going to contain infinity. So infinity is not invited into our party. And remember that what we have done so far, We have this point in the neighborhood, and we have a pre-image of this point, which are disjoint. And those, in the polynomial case, we want them finite. Okay? Now we're going to consider this family of functions. But that family of functions, we are not going to think about that functions in U, in C naught. We're going to think of that functions in this set. Look, here you have an open set. Here you have another open set. And here you evaluate all of those functions. How can I get here, let's say, infinity? So imagine that this is a rational function, right? This is a rational function. I restricted a rational function restricted to this open set. And suppose that at some point inside, right, at that point here, I evaluate this point here. So that means that I have to plug it in everywhere. And suppose somehow that I get infinity. So how can you get, in complex analysis, how can you get infinity? There are two ways that you can get infinity, right? One way is that infinity is actually sticking his nose around, and when you plug it in infinity, you get as answer infinity. That's a possibility. However, infinity is not here, right? In this set actually, oh nice, I will write it here, right? In this set, does not contain infinity. So if I evaluate, this number is not infinity, this number is not infinity, this number is not infinity, this is not infinity. So how can I get here infinity? And remember, infinity is a real possibility when I do complex analysis. And what's going on is that the only way that I can get infinity if I got zero in the denominator. If I get zero in the denominator, what means this? That means that for this point, whenever I make and iterate, I reach exactly the same point. That's the only way I can get zero. Therefore, oh, this is a periodic point. I have just found a periodic point. You say, no, you must find a periodic point in U. And this is a pre-image. Well, don't bother. Now, yes, this is a periodic point. So, if this guy equals infinity, you find a periodic point. So let's better avoid infinity. We don't want infinity in the party. What's the other special points? Suppose that you get 1. So how can you get 1? As I am telling you, whenever they are numbers, right? And if you got 0 in the denominator, you are through. So let's assume that you have no 0 in the denominator. But suppose now that this value equals to 1. If this value equals to 1, means that numerator and denominator are exactly the same thing. Well, but if those two are exactly the same thing, and this is a number, and this is a number, you will have that set equals P of set. That's not possible, right? Because what have we managed is set belongs here, while P of set belongs in the other set, right? We have shortened so that those two will not intersect. Therefore, because those two do not intersect, one is also not allowed. What else? When can this equal to 0? If this equals to 0, right, there are possibilities, right? The denominator might be infinity. No, the denominator is never going to be infinity if you start here. So that's out of the question. Well, if infinity is not involved, the only way that you are going to get a true quotient here is whenever you get, well, those are numbers, and whenever you're going to get 0, the only possibility is that the numerator is going to be 0. So what is telling this? What is telling you is that if you go one step, and if you go n steps, you reach exactly the same point. Again, that's a periodic point. And now you have to do no further adjustments, because now, in fact, you are inside U. So, unless you are mean and do not allow your function to take values 0, 1, or infinity, right? This function will have perhaps lots of periodic points, either here or here. You want them here. So if they are not here, but here, you take one iterate and the image of those will be inside the correct set. So you will say, but why should they take values 0, 1, infinity? Well, nobody's claiming that they are taking values 0, 1, infinity. But if they do not take them, they form a normal family. And if they form a normal family, they converge when we take subsequences. Well, but from here, we can solve for this, right? If we solve for this, there's a very easy equation, right? If we solve for this, we get this iteration. And you have two chances. What happens if this converges to a subsequence, which is a meromorphic function? If this is a meromorphic function, this is a meromorphic function. What happens if this converges to a function which is identically equal to infinity? Well, if it converges to a function which is identically equals to infinity, you write it this way. And if this converges identity to infinity, it still converges to set. Now, well, therefore, once this is a normal family, P, right, the iterates of P also form a normal family. But what's wrong with this? What is wrong is that this cannot form a normal family because they intersect the Julia set. And remember, if there are points in the Julia set here, there are also points in the Julia set here. Therefore, the iterates restricted to this set cannot form a normal family. And if they do not form a normal family, well, they do or they do not, I don't know, right? So therefore, that is a big contradiction. Now, what is very interesting is that what happened now if I want to lift the restriction of working in the polynomial case. So this proof works for the polynomial case because it's very easy simply not to invite infinity to the party. But if we're in a general rational function, infinity should be treated with exactly the same privileges and restrictions as somebody else. Okay? So let's give you a proof, an alternative proof that will work for rational functions. So let's take a point which is not a critical value. A critical value is the image of a critical point. How many critical points do a rational function have? The number of points that a rational function has is 2d minus 2. It's a finite number. Therefore, if you throw away a couple of points, the argument will be exactly the same and you pick another point in the intersection, right? Because I never prove it, but I already claim in the truth that that's very difficult to prove, that the Julia set has no isolated points. So therefore, if a point, the first point that you find is a critical value, you throw it away and you pick another one. Okay, so the idea, if this is not a critical value, if this is not the critical value, it's a regular point. And regular points has a full set of preimages. So if we are in degree D, it has D preimages. Therefore, it has at least 2 preimages. Right? My picture will be here. This is this point. I have this point, and I have this point. This is A. This is B, and here is my C dot here. Okay? U is a neighborhood of this one. The idea is that I restrict U to something really small. And remember, this is not a critical point, right? Because this is not a critical value. And if this is not a critical point, the inverse mapping theorem tells me that this is an isomorphism. Here again, this is also an isomorphism. So therefore, if I am careful enough to shorten this set even further, I can suppose without loss of generality, wow, because I'm working, wow, it's working without loss of generality by doing a lot much more work. That this set, its preimage, and those two are disjoint. So there are defined, well-defined branches, right? Done. And what else is that they are mutually disjoint, and changing coordinates, we can assume that infinity is not in either of those 3 sets, right? There are 3 sets, 3 disjoint sets. Its union cannot be the whole compact, the whole space, right? Because our space is connected. And if our space can be represented as the union of 2 disjoint open sets, that means that our space is not connected. Therefore, there is a point which does not belong to neither. Well, that point, change coordinate and call it infinity. So infinity does not belong here, does not belong here, does not belong here. What we will do is we're going to show or how to find a periodic point either here, well, if you find it here, you send it there, or here. If you find it here, its image will be periodic. Or here, if you find it here, good for everybody. That's exactly the place where we want. Okay? Here is very important to recall something that can be easily missed is the following. Those are not critical points, therefore they are invertible. If they are invertible, and this is invertible, I can always pass from here to here. There's a well-defined map that goes from here to here, which is simply going up by P and returning by the inverse, which is a local homeomorphism, a local equivalence, right? And that's it, right? We define the composition, right? Of course, the composition is the subscripts are only for the branches, right? Because the iteration is the universal iteration that we are considering. F and P are exactly the same, right? So this function goes from one set to the other, taking a shortcut. But in truth, it goes up and goes down. But we actually think of that actually as a function that goes from one to the other. Remember, all those three elements are different. So that means that if we take set in one set, P of set in the set U, or we take gamma or phi of set here, right? Those three elements are different because they belong to different sets, right? As I told you before. Now, what we're going to define is this function. Okay. Neither set P of set of phi of set are equal to infinity. Those belongs to that small set, right? And here is the wolf waiting actually for somebody to do something wrong and eat it. And this is the guy that is going to blow. What happened? And remember, where are you starting? You were starting in a set like this, right? You were starting and here, and the image is here, and that's on the other side. You are starting in set here. You take a point. Of course, the first step is going to send you to U, and then n equals to 2, 3, 4, 5, 6, 7. The point goes a lot of places, and the point most probably, not that point, but some point will probably hit infinity. So what happens if this point, as it may happen, is sooner or later equal to infinity? Well, that's an analytic function. And if this is an analytic function and this point is equal to infinity, it's the only point in this neighborhood which is equal to infinity. And therefore, you can rewrite this, right? You can rewrite this as 1 minus phi divided by phi divided by Pn divided by whatever. Hopefully you understand what's going on here. Right? If this is infinity, you divide this numerator by Pn, and this denominator by p iterated times n times. Therefore, at that point, that equals to 1. So when this point hits infinity, the value of this function equals exactly this. And those are 3 numbers, right? Because z belongs to a finite set, p of z belongs to a finite set, and phi of z belongs to a finite set. So if for one reason or another, the image at some points equals infinity, the value of this function should not be calculated replacing infinity here, but only looking at this part. Again, when this hits infinity, this can be 0. Well, those are numbers, right? And those numbers can only be 0 if numerator equals to 0. And the only way that they can be 0 if is z and p of z are the same point, and they are not because they belong to different sets. What else? Can they be infinity? Well, when can a quotient of numbers be infinity? Only if the denominator is infinity, only the denominator equals to 0. But the denominator is never 0, because the denominator is a point here minus a point here, which are never equal. And again, this quotient can be 1. No, this quotient cannot be 1, because it can only be 1 in a quotient if and only this numerator equals denominator. We cancel p of z, and then it will be possible if and only if the point here equals its image, its mirror on the other side. Therefore, our only worry, which was the treatment of infinity, or when this point takes infinity, is not worry at all. But because the point can hit infinity, but this function will never be 0, 1, 0, 1, or infinity. So again, we start asking exactly the same questions. When does, remember, infinity is out of the picture, right? Because if it hits infinity, I will miss 0, 1, and infinity. So whenever I am with numbers all the time, what will happen? Whenever I'm with numbers, the question is when I will hit 0. I will hit 0 only when numerators are equal, the numerator are equal to 0. So that means when this point and this point are the same. Never, right? So when this point and that point are the same. It's sort of easy. This is sort of nice, because here you are taking this point, right, in that, and here you are taking n step and reaching this point. Those are exactly the same point, right? So what's the next point? The next point will be this one, right? That means that this point will be periodic. Again, when this fraction will be infinity, this fraction will be infinity with either of those is equal to 0. Again, those two are very easy to check that they are different, right? One belongs to this set and one belongs to this set. Actually, the image of this is this one. And the other one, possibility for the denominator to be 0 is that precisely this point, the point here, and its image, and actually not its image, but its nth iterate are exactly the same. But if they are exactly the same, this point is periodic, and therefore this is periodic too. And our last possibility is when is going to be 1, is going to be 1 if and only if numerator equals denominator. And as you can see, that will be, it looks sort of complicated, but it's not. Because look, in numerator it appears p to the nth, and denominator also. And the numerator it appears plus 5 multiplied by z, and the denominator also. Therefore, you will have two terms matching those two terms, and those two terms will represent, again, a very easy equation. And well, to finish our session is a very nice and elementary proof of how to construct a rational function which has no Fatou sets. And the idea is as follows. We're going to consider a complex torus, but instead of considering a complex torus, we're going to consider its universal covering. And at this universal covering, you imagine the complex plane, or even you can consider R2. And in R2, oh, no, it's better with the complex plane. And in the complex plane, you mark the Gaussian integers. All complex numbers of the forms A plus BI with A and B integers. That's a lattice. And in that lattice, you consider parallel lines. And the idea is that considering parallel lines, you, for example, start doubling the points. That's good. I think doubling the points is good enough. Okay, and here it's very easy to prove how you get periodic points. And you get actually periodic points by the same arguments, by the same reasoning where you get periodic points in the circle. And because your map is expanding, you have that the multipliers of all of those points are going to be repelling. But take a careful look. Periodic here means that if you start in a piece of fundamental domain, and you double things, you're here, you finish here, right? So actually, for example, you double it, you get here, you double it again, and you get here. So, but this point in the torus is exactly the same point. That's what periodic means. But look at this is like doubling, right? And if you double things, your multipliers are going to be multiplication by 2. And whenever you get multiplication by 2 as multipliers, then you have expansion, you are repelling. Okay, so you do that in such a way that all points are periodic. Not all points are periodic, but all periodic points are repelling and they are dense. But this is the torus, right? Right, and then you got your scissors here, you got here, you got here, you got here, and you paste as usual that, and you got your torus. And you got an iteration in the torus with a dense set of repelling points. That's no news, but that's not exactly what we wanted to do. What we wanted to do was to construct a rational function which has no Fatou set. And the way to do that is, once we have done this, right? All multipliers are in norm bigger than 1. Actually, all multipliers can be done equal to 2. if you wish, because the doubling map is good enough. However, look what happened at antipodal points. If you have a point and you double it, and you got the antipodal point and you double it, you got antipodal solutions. So therefore, you can make in the quotient, in the torus, an equivalence relation that actually matches a point with its antipodal. And the answer and its image will be exactly the same class. Well, not will be exactly the same class. Will be a class of antipodal points. However, what's the orbit space of antipodal points in the torus? It's very easy to check. This is my torus, right? I am considering antipodal points, right? This point here is antipodal with this. What else? This will be antipodal to that. So therefore, this is a fundamental domain. What's the antipodal of, I will say, let's cut it here in the middle. More than cut it, let's consider an imaginary cut in the middle. And the antipodal of this point will go through the other side, right? Will be here. And therefore, in order to match antipodal points, you will have to paste this half with this half. Here again also, the same. Those two are antipodals. Oops. And here, you will get antipodals. So bring a napkin from the kitchen and close it, and what you get? A tetrahedron. And what's topologically, or what is in complex analysis a figure which is equivalent topologically to a tetrahedron? Is a sphere, and in sphere there's only one. So therefore, what have you constructed? Because everything descends to classes, you will have that the orbit space is a sphere, right? There's only one sphere. And what have you constructed? You have constructed a rational function for which the periodic repelling points are dense. But we already checked last class that repelling periodic points belong always to the units. This is called, I don't know, I was sure that it was lattice example. And if I'm wrong, if I am not wrong, this example is even before Julia and Fatou. So this is a very old example in which, not knowing exactly what's going on, right? We got a map in a rational function which is repelling. And you know what's the nice thing? That this can be done very simply, right? Because this is a fundamental domain, and you can construct in the Gaussian integrals multiplication by 2, and you can actually perform the points, and you can check what will be the behavior of the critical points, and you can write down equations. And it happens to be a degree 4 equation with coefficients where you can calculate. Actually, you can construct this in not only in the standard torus, right? You can construct this in a whole family of torus. Even if I'm not wrong, there are several torus that allow more examples than other ones. And well, that was all I was planning to tell you in 4.5 hours. This is essentially, when this is taken as a graduate course, is usually 3 or 4 sessions or 3 or 4 hours a week in a full semester. And actually, we have touched only the surface, and there are a lot of details that you can go and must go deeper. And I don't know if there's any question. Juan?
What was actually expansive? What you meant by expansive?
Expands. Multiplication by 2, it expands.
Okay. Okay.
Right?
Okay.
And actually the multiplier is 2 everywhere.
Okay. Just okay.
The derivative is 2 everywhere.
Yeah.
So when you have a period 3, your multiplier will be 8.
Yeah.
In a next point, the multiplier will be 2.
Okay. It's just I was just wondering if there was a condition, like exact condition on the matrix to say this is expansive.
No. This example works so good that it's actually no tricks behind. Expansive and multiplication by 2. And what's your idea of expansive? Multiplication by 2.
Multiplication
right?
by 2. Okay. Yeah, okay. Okay. Yeah, okay. Thanks. Yeah. No, just for a moment I thought of I know it's unrelated. It's just I thought of the classical map 2-1-1 something like that, but I don't know if that gives you anything or not. But,
Sorry, again.
I just said that for a moment I thought only of the map, the Arnold map, like a 2-1-1 thing, like. Yeah, it's not something. Yeah, like I just was wondering what happens if one change the map for a matrix in general, but I don't know.
Well,
but,
you're getting into deeper waters.
Okay. Yeah. Okay. Okay. Thanks. Are there any questions?
Okay, Alex, the slides of the course, where are they? Okay.
Okay, and then I think I should thanks. Okay, it's my turn to thank Professor Poirier by the effort that he gave to give this wonderful course and to be recorded on YouTube by the part of the organizers. I don't know, Alex, I think we are going to wait or how? I don't know. Wait, I funded the course. We have some break, right? Yeah. Until 4 p.m. to to Matthieu Arfeux. To Matthieu Arfeux. Okay.
I think I don't know if I'm gonna speak in Spanish or in English. What do you think?
No, if I'm not wrong, everybody's here in Spanish, so podemos
But I saw you were speaking in English, so that's why I'm not sure.
Lo que pasa es el doble fin, ¿no? Sobre todo para los locales que se vayan acostumbrando en que tienen que... tú estás preguntando si tú vas a hablar en castellano o en inglés. O si compartimos un rato en castellano o en inglés.
Bueno, veamos si hay alguien otra persona que no sea de los estudiantes que se conecta, voy a hablar en inglés. Si no, voy a hablar bien castellano y en inglés voy a hablar en chileno.
Mientras no hables en francés.
Chileno.
Porque Milnor se estaba conectando en las tardes.
Ahí vamos a ver. Está el Víctor. Ya, así que ahí veremos si se conecta Pascal, todo eso, porque puede ser que les interese esta cosa, pero ahí vamos a ver.
Linda King también estaba conectándose.
Sí, se estaba conectando. Así que voy a ver, pero yo tengo los slides en inglés, a mí me da bastante igual, la verdad, solo que no practiqué el inglés por un buen tiempo, así que ahí vamos a hacer un test, a ver si se me olvidó o no.
Pero cómo hablas inglés? ¿Como francés?
Ah, como los chilenos el español. Así que nos vemos en un ratito.
Ya. Yo me desconecto porque yo estoy, ahorita estoy en provincias y estoy colgado con el teléfono de mi esposa. Entonces regreso yo a las 4 para tu charla.
Ya, yo también me desconecto para conectarme con otra cosa. Me conecto en 15 minutos más. Chao, chao.
Bueno, 3, 4. Okay. I think I should introduce you, I guess. Okay. So we continue with the talks. Right now we have the talk of Matthieu Arfeux from the University of Pontificia Universidad Católica de Valparaíso. He has done his PhD at Université Paul Sabatier at Toulouse, and he will and he's now a professor at Pontificia Universidad Católica de Valparaíso, and now he's going to give a talk on I'm sorry, what was the title? Is
Jumping between trees.
Jumping between trees. Yeah. Thanks. Okay. I let you talk.
Well, thank you for the introduction, and thank you for giving me the opportunity to talk about some work. So basically, during this talk, I will try to discuss a bit more about the curves that Araceli Bonifant has been talking about. So somehow the difficulty for me is that there was a talk of Araceli before me that was introducing this stuff, and after me there is a very interesting talk of Jean Kiwi, which is gonna like steal the end of my talk. So I'm gonna try to just stay in between the two things and give some historical accounts about my work with Jean Kiwi. So I know that not everybody has been participating to Araceli's talk, maybe. So I will go back to the introduction and try to do things like informally. I hope that my talk is going to be informal. So I will try to, during this talk, to give some ideas or some techniques to make you be interesting in looking at some complex analysis, techniques, etc. Even if I'm not going to be precise a lot. Yeah. So just giving some idea of some tools existing so that students get interested in some stuff. Yeah, quite different than what Alfredo Poirier has been talking about somehow. Yes. So we're gonna talk about cubic polynomials. So for cubic polynomials, so to do dynamics, usually you do everything modulo conjugacy by Boundedness transformation. So there is a natural way to think about cubic polynomials as this family here, which is z cube minus 3a squared z plus b, and you identify all the polynomials to the parameters a, b. Yeah, it's almost the same family as Araceli, so I just have a change of names on the variable somehow. And so this family, the way to write this family is to make precise what are the critical points. So the critical points is where the derivative cancels. Yeah, and I think that during Alfredo's talk, you already saw some critical points appearing, and that it may be interesting for dynamics to introduce them. And within this set, which is two-dimensional, we want to study some slices. So the slices are called per n of 0 or per n or Sn sometimes, which are the set of parameters such that the plus a has exact period n. Okay, so you choose one of the critical points, which is plus a in this case, and you force it to have exact period n. And so the conjecture of Minor, maybe I should say theorem, but the paper is still not published. So in 91, Minor conjecture that this is an algebraic irreducible curve. So somehow, if you think about this, it's kind of easy to see that it is an algebraic curve. So if you want to say that an iterate of the polynomial, so an iterate of the polynomial, you can compute what it is. You can put plus a on it, and you divide by something to say that it has exact period n, and you see that it's naturally an algebraic equation. Okay, so it's clear that it is an algebraic equation, and somehow the degree of this equation is quite high if you think as composing n times the polynomial to itself. It's a kind of high degree. So what is nice about this this thing is that you are getting a polynomial of very high degree. So if you can take any arbitrary degree n, so not exactly, but very high degree n, and you will have an algebraic curve which is irreducible, meaning that you cannot factorize this polynomial. So I'm sure that all of you made some algebra before and check that to see that something is irreducible. A polynomial is irreducible is something which is kind of difficult. Okay, so it's a very nice thing. So Minor proves that it is true for n equal 1, 2, and 3. And in a paper with Raissy, Bonifant, and Jan Kiwi, they made computer evidences that it is true for n equal to 4. Okay, and you will see why n equal 1, 2, and 3 is kind of normal. Yeah. So why this curve is important, I think you already asked, and John Miller said some answer, but I may add some things. So somehow the cubic polynomials have been studied like systematically by Bonner Hubbard in like a very interesting paper, and they show that these are very important in space. Okay. And also this kind of the cubic polynomials also have a structural importance in non-Archimedean dynamics. Maybe Ian can say something about this later. And it is nice to think about this curve as a natural ground for testing some tools that we have for the Mandelbrot set. Yeah, because somehow the dynamics is related to what are doing the critical points. So in degree 2 polynomials, you just have one, which is not infinity, and which is somehow free. So depending on where is the critical point, what it is doing, you have distinct dynamics. And for cubics, so what we're going to say we have two critical points which are not infinity. Thus, we're going to fix what is doing one and say what's going on depending on what is doing the second one. So looking at this curve, we fix one which is going to be of period n, and look at what is the other one doing. And we expect that tools from quadratic dynamics are going to be able to be used for this case. Yeah? In this sense, it is a test ground for generating the tools. Yeah, and as I say, it's an algebraic equation, so it's important. It's some question which goes maybe outside of just the complex dynamic setting. Yeah, because we're talking about algebraic curves, etc. Okay. So as I already said, so Minos already proved that it was a smooth affine curves. And we can ask what is the genus of a smooth compactification of pair n? Yeah. So in the paper with Raissy and Jan, they gave a formula for the Euler characteristic of pair n, and also DeMarco and Schiff made an algorithm to compute the number of punctures of pair n. So you have algebraic curves; it has to touch infinity, and this is called punctures. And you can try to compute these kind of things. So they give an algorithm, but somehow we don't have like a systematic formula giving an n what is going to be the result. You have to make some computations. And this work is based on old work by of DeMarco with first with Mark Muller and then with a lot of paper with Kevin Pegrin. Yeah. So you already heard about what is a Fidula set. So this is a set of points which are not going to infinity under iteration. And one can check that if the free critical point, which is minus a, has bounded orbit, then it's going to be connected. And if it escapes, then the Julia set, Fidula set is connected. Okay, we're going to give some explanation about that later. going to be somehow. I'm going to talk about that again later. So just think about that first. So you have this dichotomy, and then you're going to have a dichotomy in the parameter space related to this. So you say that the connectedness locus is where the feed Julia set is connected, and the escape locus is where the critical point goes to infinity, the free critical points. So the first result of Van and Herbart, which is quite old right now, was a long time ago, is that the set is compact, the connectedness locus. And another result that has been mentioned by Raissy is that the escape component are isomorphic to a disk minus a point. So you can think about escape component to have in the border, in one border the connectedness locus, in the external border, and the point 0 that is missing is the part which is going to infinity in the parameter space. Okay. So we get some pictures of this set. Maybe there is some involution involved. Let's say that the picture is the right one, but I'm cheating a little bit. So this is for n equal to 1. So you have a nice picture. And of course, if you have such a picture, you can see that the genus is 0, and you can check that it's connected. It's simple proof. You have parametrization. It's a plane minus a point. So the escape region in my talks are going to be usually in blue. And here you see that you have like a disk, which with one border, which is the black region, the border of the black region. And there is a missing point, which is infinity. So you see that it's a disk minus a point. Escape region, yeah. So that's the first example. Second example, when n equal to 2, also you have a parametrization. So maybe you have in the other talk you had a double cover of this picture. So I'll say I'm cheating a little bit. And you have two blue regions, and you have to imagine that this region you have to remove this point, which is at the center here, yeah, which is a point going to infinity. So this picture is looks plain, but like a plane, but it is something embedded in a two-dimensional complex setting. Okay, so that's also proof that it is connected. Yeah, and for n equal to 3, you have this picture again. So in the case of not cheating picture, you will have a torus, but in the cheating setting, you have something which is like a plane minus some points. Okay. And as you can see here, you have many escape components. Yeah, you can count them. In this case, in this picture, you have 6 punctures, one in infinity and the other ones. And for n equal to 4, one can see that it is genus 6 and 14 punctures. So you can have like a picture like this one. You can make like local drawing and check that things are how it looks like. Yeah, and also put like in black the connectedness locus, and in blue the escape locus. Okay. So the idea to prove the conjecture is saying that knowing that it is smooth and connected, then it is irreducible. Okay. So the smoothness has been proved. So usually you just have to prove that it is connected. So the way to prove that something is connected is to make paths within it. So you take 2 points and try to make a path between them. Okay. So we're not going to take any 2 points. So we're going to make the remark that the connectedness locus is compact, so the black region, and every irreducible component has to touch infinity. Yes. So you cannot have a component, a connected component of this space which is all black. Yeah. So every connected component has to have a blue region. So this is what I'm saying here. And let me just remove this. So it is enough to show that the escape component, all of the blue region are in one connected component to prove that the space is connected. Okay, somehow we're going to forget about the black part and get concentrated, get thinking just about the blue parts. Okay. So the way that Raissy, Jan, and Jack were doing it for degree 4, and that they make local pictures, they put numbers or names for all of the blue regions and try to check with local pictures that all of the blue region can be reached by paths between other regions. And they make a little graph and to try to give the structure of the escape region in this curve, and to see that all of the escape regions are connected somehow. I'm not giving more details than this, but as you can see from this, a way to prove that the space is connected is the first step for this is to give a name for the regions, so that you can check that you can reach all of the region after a certain number of paths. Okay. So as I say, before traveling, you have to label the components. And what we're going to do is to label each escape component with a quadratic polynomial and escaping trees. Yeah. So let me talk about this. So here you have some example of what you see in the blue region. So in green you can see the escaping region. So the basin of infinity. Yeah, and purple you can see other stuff, so the Fidjul assets. Yeah, so in all of these things it is disconnected, and you can see there is 8 pictures that maybe I will talk about again later, that we're talking about, that Raissy was talking about. So one theorem I thought that Alfredo was going to talk about, that it seems that he didn't, which is kind of important for polynomial dynamics, is this proposition of Butcher, saying that on a neighborhood of infinity, the map, the cubic polynomial is projected to z to the 3. So if you have a cubic polynomial, somehow when z is big, p of z is kind of the same as z cubed. Yeah, and you can make it more formal by saying that you have a conjugacy. On the right, you have z cube near to infinity, which maps circles to circles and lines, rays to rays. And by the conjugacy, you can say that you have kind of circles also for polynomials and rays. Yeah. So these maps are called Butcher coordinates, and you can see, we're going to talk a lot about rays and level curves. So the level curves are the circles. And in infinity, apart from a black region, yeah, outside of compact sets, you have like a dynamic of the cube. Okay. Okay. And so what happened? So if you wanna, you say yes, near to infinity you have something like this, and you want to extend. The first thing you wanna do is to extend this as much as possible. So what you're gonna say, what you're gonna see on the right picture, when you have the cube, you can take pre-images of circle or of disk, and these are gonna be disk, and you can extend this until you get the dynamic outside of the unit disk. Okay, because every point outside of the unit disk goes to infinity, so you can iterate and then go back, and you're gonna check that this dynamic is well defined outside of the unit disk, and every point is going to infinity, so you wanna do the same on the left. So what happens usually if you don't have anything bad happening, the pre-image of a curve like this is going to be a curve like this. As the pre-image of analysis is going to be analysis. So what can happen to be, what bad can happen? Sorry. So what can happen is that you have a critical point. Yes. Why critical point is problem? Because somehow the derivative is 0, so you don't have local homomorphism. Yeah. So if the derivative is not 0, there is no problem. You can take the pre-image of the image, and everything is going well. Yeah. Well, but what happens if you have a critical point on such a curve, a blue curve? If you have a critical point of such a critical value, sorry, the image of a critical point on a blue curve, then the pre-image is going to be 8. Okay. So this is what is on the other side. So if the Fidjul set doesn't have any critical point or any critical value, you can take the pre-images, and all of the circles are going to be circled, and you can extend the map, the Butcher coordinate in all of the basin of infinity. Okay. Whereas if you have a critical value on the circles, then you take the pre-image, and you can have a curve like in the blue one. Yes. And of course, if you have a pinching here, you also have like two rays standing at this critical point. Of course, this critical point is -8, which is the one that goes to infinity. And you see that on the left, the Fidula set is a complement of a disk. So puncture disk going to infinity. So somehow the Julia set is going to be connected. And on the right, you see that by the 8 picture, you can check that already you have two components of Julia set, one on the left and one on the right. So you can see that effectively, if -8 goes to infinity, then the Julia set is disconnected. Okay. So on the right, this is a picture of something in the blue region, and on the left, this is something on the black region. So let's talk about the blue region, which is going to be the one that we're going to focus on. So there is this proposition by Hubbard, which is kind of fundamental in holomorphic dynamics, that says that if you have a domain which closure is included in the image of itself, such that the map restricted to U as a grid 2, then somehow the map is equivalent to a quadratic polynomials. So there is a way to associate with such a configuration a quadratic polynomials. You can see on the left the pictures that I had before. There's these 8 pictures. And so the image of the 8 pictures is going to be a circle which is green outside here. And so I put it on the right, and you can check that the blue region, where you have the critical point here, maps to the purple region in the way of the proposition above. So you can associate to this map a quadratic Julia set, and you can check that this is this map here is like is a rabbit. Yeah, you may have I've seen a rabbit before. Looks like a rabbit, and it's named a rabbit. Okay, but we can have some other stuff. Yeah, which is the quadratic polynomials. So instead of saying about just quadratic polynomials, you can check that. For example, in this case, you have a quadratic polynomial with a critical point which is periodic, because we are in the setting that you have a periodic critical point. And quadratic polynomials with a periodic critical point are very well studied and well known. So there is a notion of Hubbard trees. So if you take a quadratic polynomial with a super attractive cycle, a critical point which is periodic, you can make a, like, so in this picture it is the red point, which is the period of the critical point. You can make a convex hull of this orbit. Here is, let's say, legal convex hull, saying that you have a way like to define it like a unique way, which is nice and somehow dynamical. And this is called a Hubbard tree. And why it is important is that every quadratic polynomials with a super attractive cycle is characterized by its Hubbard tree. Okay? So somehow, instead of saying that I have a Hubbard tree associated to an escape component, a quadratic polynomial associated to an escape component, I will talk about the Hubbard tree of this escape component. So this is one of the trees we're going to be on and jumping from. Okay? So this is somehow, these trees are very about quadratic polynomials which are connected. Okay? So somehow this is a tree related to connectedness locus somehow, yeah, for quadratic polynomials. So these quadratic polynomials correspond to a polynomial which is within the connectedness locus of quadratic polynomials, which is called the Mendel set. Okay, so this is not talking about escaping somehow this tree here. And I said that we're going to have a Hubbard tree and an escaping tree. So let's talk about the escaping tree. So on the left side, you remember that you had this close to infinity, and then taking a preimage, you will have 8 pictures. And if you take a preimage of the 8, you can have some other stuff going on. And this is going to give me other picture like double H or something like this. Yeah, and what is not drawing, what I hear are like circle. So what is a De Marco-Macmillan escaping tree? You think that every time you have a level curve, like a circle, yeah, say a level curve, you're gonna collapse it to a point. So if you are close to infinity, you have just circles, so every circle is a point. And you can see that when you move from infinity to this curve, for example, you're gonna have just points every time you hit a level curve. So this is what is represented on the right. So when you are close to infinity here, you are just one level curve. So you have 1 point and you move continuously from one circle to another circle. Like this thing looks like a big annulus. And then when you hurt this level curve, well, this level curve has just one connected component. So this is just 1 point, but going down from here, you're going to have one level curve on the left and one on the right, yeah, which corresponds to the same level. So you can see that somehow after this point, corresponding to this 8 curve, you're going to have, again, annulus, but one on the left and one on the right. Okay, and then you go to this level, and after this level, you have like 2 on the left and 3 on the right. Yes, and so you have a picture which is called a DeMarco-Macmillan escaping tree. Of course, the circles, by the Butcher coordinate maps to circles, so you can define dynamics on the level curves, and this defines the dynamic on this tree. And suppose one of the work done by DeMarco, Pilgrim, and DeMarco Aronschiff are to enumerate the trees to count escape components. So it's a bit more complicated than these trees. You have more things to talk about, but one of the first steps is to talk about this tree. And this tree is a tree really talking about escaping things. Okay, you're just talking about what is not, what doesn't have bounded orbits. Yeah, what's going to infinity. I don't know if it's clear till here. If there is some question, I cannot read, but you can open the microphone. Yeah, so these trees are one tree talking about the escaping things, and another tree talking about the things that are not escaping. Okay. Also, something that you can check, well, that mentioned is that, so here I put it in blue, these 8 pictures and the 2 other green ones. Yeah, the one, well, so the picture on the left here is the one that was on the other slide. And of course, when you have something pinching, you have rays going and collapsing to this point. Okay, so one can check that if you know how these curves are, the DeMarco-Macmillan trees with these curves, you can also know it from all of the rays that are collapsing to some points. Okay. Of course, knowing this picture is the same as knowing the one on the right. Okay, somehow knowing what the rays are doing is the same as knowing what the level curves are doing for the escaping tree. Right. So as I said, so there is a DeMarco-Schiff theorem that gives you an algorithm to compute the number of punctures. And what do? Is that they do a bit more than doing these trees. They give some more combinatorial tools, but based on these trees remark. And with this, they are able to compute the punctures. At the end of the day, they are not able to give a unique name for each escape component. So there is still something missing, that to give a label to every escape component is kind of difficult for the moment. We don't have any way to do that, but with the tools we are able to count them. Okay, so we give, for example, one tree, special tree like of DeMarco-Schiff or DeMarco-Pilgrim tree, and we are able to say how many escape components have this tree. Okay, this is what they are doing, but they are not able to give one for each one. Okay. So let's talk about the first idea, to move from one escape component to another escape component. This is an idea I got in my PhD, but I've been waiting for long to publish it, and at the end of the day, it's never going to be published because we did all the stuff after this, which is an improvement. But as I said, I'm going to say about the history of all of these things. Okay, so what is the first idea to travel between escape components? So you have these blue regions. Let me go back to the pictures at the beginning. And so what you want to say is that there's a way to go from one region to another region by crossing some points. So if you see this region here, which is called the rabbit region, because you have the herbatry is a herbatry of a rabbit, and you say that, okay, you have some common points in the border. And if you check what are these points, these are parabolic dynamics, which is something we're going to talk later. I mean, you already heard about that with Jasmin this morning. Okay, so we're gonna look at these kind of points and try to perturb them and saying, from this point I go to an escape component and to another one. So you can go from this escape component to this one. Both of the escape component are the same connected component of the big curve. And doing like this, you hope to be able to make enough paths to connect all of the escape components. Yeah. So what is the idea? To find some special type polynomials and to perturb them different ways and to be able to identify the two escape components you go to and say that you have enough such polynomials to connect all of the blue regions like this. Okay? And so what are the special polynomials you're going to look at? And these are the one called intertwinings. So the intertwining surgery has been studied by in a paper by Epchaniopolsky and another one by Raissy. And what they are talking about is cubic polynomials that contain two intertwined copies of quadratic Julia sets. So we say, well, I can believe this because one quadratic Julia set has one critical point, and if you have two quadratic Julia sets, then you can have two critical points. So you believe that you can get from two quadratic polynomials something which has degree 3 because polynomial of degree 3 has 3 critical points. Okay. So how do we do this? First of all, I'm gonna be in the setting of Helsinki because we're gonna intertwine a Julia set with a periodic critical point. Of course, because I wanna get something which has a periodic critical point. At the end of the day, I wanna be on my curve. Usually in my picture it's going to be in purple, and a periodic Julia set with a parabolic fixed point. So parabolic fixed point means that you can perturb it, and you hope to be in outside of the connectedness locus. Okay, of course you can perturb it in a way that you stay inside. This is point where you usually can have several perturbations, and the dynamics are going to change a lot. Yeah, this is what is having a parabolic fixed point. Yeah, so let's start with a quadratic Julia set with a periodic critical point. So this one is called a hairplane. It's just a small picture, but it's one with a periodic critical point. Yes, and the Julia set looks like this one, like this picture, and you can understand why this is called an airplane. Okay. And on this thing, you choose a point here, and you look at the rays that land at this point that's put in red. Okay, you have a quadratic Julia set with a periodic point in the Julia set, then you're gonna have a cycle of rays that land to this point. Okay, and so what we do, and that we cut along these two rays. Okay, we're gonna have this picture here. We cut and we open. So to imagine that here you have nothing. Okay. Then you said, well, I want to have a Julia set which is parabolic. Yes, let's forget about what is being parabolic with a fixed point, such that the combinatorics of this one map to this one and go back agrees with this one. So there is one, and because we know a lot of the model set were it's very easy to find the one that's gonna work for this. And in this case, it's gonna be the basilica. So if you cut this vertically in two, you're gonna see that it looks like a church if you put it. So this is why it's called a basilica, because somehow it looks like a church. And you put it inside. So somehow you see that when I put the black one with the purple one, somehow the dynamics have to map this part to this part, yeah, and this part to this part, because you want to agree with the dynamic of the red ray that you cut it. Okay, and somehow the theorem of Raissy says that in this case you can do a polynomial that is gonna look like this. Of course, it's not gonna look like exactly like this, because as the preimage of this point, you have to make a similar surgery, so you have to adjust all of the preimages and make it work and make it conformal. Okay, so the way to do this kind of work is using something called the quasi-conformal surgery. That is a big topic to study, and using like this quasi-conformal surgery, you can make by hand some polynomials. Yeah, everything is based on theorem of Alfaux-Beers, etc. And somehow this quasi-conformal surgery is what made all of the holomorphic dynamics going back on the scene in the 80s. Yeah, so when they discovered this kind of surgery, then we had a lot of new papers and all of the Cody Hubbard stuff, and a lot of new papers that were talking about holomorphic dynamic appearing. Yes, in the 80s. And so if you do that, so I'm not gonna get this picture exactly, but you're gonna hit something similar, which is this one. So you see that in purple you have a cycle period 3, a critical point, and you have an airplane here, and at this point you're gonna have a parabolic Euler set, and of course you're gonna have preimages of the airplane somewhere else. So you have, of course, to think about taking all of the preimages to make it work. Yes. So this is what is intertwining between the airplane and the fat basilic. Okay. So let's try to perturb this intertwining. So if we wanna perturb this, somehow the part which is in black is gonna be transformed to something else, a discontinuous way. Okay. So there is a way to perturb it so that as this black region here, which contains the critical points, the 3 critical points, you have like 2 rays that map to the same image. And there is a way to perturb this dynamic so that this ray is going to connect to this one. Okay? So if you perturb this, as you can see, you're going to have these 2 rays landing at the same point. And if you imagine that this is a critical point, then the 8 pictures that I said that we were talking before, you're going to have 1 circle here and 1 circle here. Okay? In particular, you see that on one part of the 8, you have like this airplane, which is still here. Like it's have bad points, going things weird, but still you have like an airplane. Okay, so if you try to check what is the herbartry of this thing, it's gonna be the herbartry of the airplane. Okay, but there is another way to do that. It's connecting this ray to this ray. So again, 2 rays that are landing on the border of this component, and you can check that if you do that, then the airplane is not in this picture. Why? Because if you have the 8 pictures here, so there's 1 circle on the left and 1 on the right, and on the picture of the left you have some iterator of the critical point and some on the other one on the right one. Okay, so what we can say is that perturbing through this ray or to this ray, you're gonna go to 2 different escape components. So on the right you have the parameter space picture, at the center is intertwining pictures, and you have a way which is in pink corresponding to perturbing, so that the critical point is going to be on the pink ray, and the ray parameter ray, the yellow parameter rays corresponding to having the critical point on the yellow parameter, yellow dynamical ray here. So what we did is exactly what we wanted. We had a point in the parameter space, and we had 2 different ways to perturb it, maybe more ways to perturb it. But doing this, you have you reach 2 different escape components. Yeah, and somehow you can see that as you have 4 rays landing here in the parameter space, you're going to have 4 rays this picture. Okay. Oh, so I forgot to talk about what I was thinking about talking about. Is that I'm doing a little more. So if you see this picture, you know what are the two rays that lands at the critical point, right? So there is, you know what is going to be, how is going to be the 8 pictures, and somehow, as you know what is the dynamic before in here, you know what are the pre-image of this on the left and on the right, and somehow you're going to be able to, let me go back to a bit above. You're going to be able to find this picture of the rays, yes? So there's 2 rays landing at the critical point. You have the pre-image which is going to be on the left and on the right. You know how the curve looks like, or how the rays looks like. So somehow from the interturning picture, you're able to know what is the escaping tree of the region, okay? And this is why I was talking, I was saying, yes, I was saying that I was talking about jumping between trees. So somehow I have a tree here, which is a Hilbert tree of a quadratic Julia set. And from this one, I construct a cubic polynomial. And then from this thing, I'm able to find escaping trees. So this is what I like about this work, that's not being published and never going to be published somehow, is that you give a relation between Hilbert trees, which are talking about the connected locus, connected thing, and the escaping tree, which is something about escaping sets, okay? Not connected stuff, okay? So let's talk about a bit about how to perturb this. Yes, so you're gonna be able to perturb it, but let's do it. So for this, I had a work with a two equation, which is not published and not available, but it's somehow some work that Tsui have been doing for years and adapted to this situation to be able to perturb parabolic polynomials. And so I've been waiting for a long time to work with Tsui and finish this paper. That's why many other papers are not being published. But when I've been working with Jan, we found out a way to make it more easily. Okay, so in which sense more easy, just using Orsi nodes. So in our paper with Jan Kiwi, we make a perturbation of parabolic type of polynomials like this one on this curve using Orsi nodes. But still, I think it's interesting to talk about this work about parabolic explosion because it gives you some ideas of how the parameter space looks like. Okay, so I'm going to talk about this, even if it is not the tool that at the end of the day one use. So what do we prove with Tsui is that if you have a parabolic parameter, so a polynomial with a parabolic point in the connectedness locus, and an array adjacent to this parabolic point, then there exists a corresponding ray landing at this point in the parameter space. Okay? Somehow, what is nice about this is that you give a parameter space from the parabolic, from the landing point. Okay, so you have a point and you find a parameter ray that lands here. And this is kind of new because usually what the theorem were known is about saying that some rays land in the border of an escaping, in the border of an escape component. Okay. And so somehow this part is kind of more difficult. So let's say what are adjacent rays. So when you have like two intertwined polynomials like this, so in the black you have the parabolic dynamics, and in the purple you have where it is where you have a periodic critical points. And as Jasmin said, you have some petals that are defined. Like she has been talking about the Fatou flowers, low Fatou flowers. And so somehow you have some nice petals that are defined. These petals come from the study of parabolic points. And as you have, like you see the picture, is like kind of a rotation by 3. Looks like a rotation by 3 around this point. Okay, so you can imagine that you have like 3 different regions here that contain some important information. Yes, and you're gonna say that rays are adjacent if they go to the 2 regions that are next to this critical point. So you have the region of the critical point, you have just 2 petals that touch it, okay? And the rays are gonna be said adjacent if they go through these 2 regions. As you can check, there are, in this picture, only 4 rays that intersect these 2 regions. So 1 above, 1 here, and 2 on the bottom. So you expect that this say what Raissy was talking about, that in the parameter space you can have at most 4 parameter rays, at most 4. Okay, this is not a proof, but this is an idea of how where the things come from. Okay, that at most there are 4 parameters, parameters ray landing at the parabolic point. So you look at these petals, and somehow here you have a dynamics which is conjugated to translation by 1. If you remember what I was talking about, Jasmin. So you look at the 4 rays, and you can see that in the parameter rays, parameter space, you also have just 4 rays landing at this point. Okay. So you have so in these regions you have translation by 1, and somehow the fundamental domain looks like a crescent, crescente, no sé cómo dicen en Peru, French cuisine, and these are the fundamental domains. So if you just look at the fundamental domain here and the fundamental domain there, etc., then you're gonna have something like this. So actually, if you think about the flowers, you had more stuff than what is showing here. So you have these petals here, which are the repelling petals, and you also have some other petals that were going in between here. Sorry, there, and there. Sorry, I'm talking very informally. Yeah. So these are the repelling petals, and the other ones are called the attracting petals. You also can take some fundamental domains there, and you're gonna get some petals like this. So this is in the back region where you have an interrupt of the critical point that have to hurt at some point these petals, and these are one of the ones that were drawn before. As you can see, you have some external rays going through these regions and more stuff. Okay, and you have 3 of the one on the left, 3 on the black region, and 3 on the other region. Okay. Of course, this thing, if you think about a bit of fundamental domain, this curve maps to this curve, so you should think of this glued together, and you have cylinders. And so what we do with Tsui, it's saying that you should glue this cylinder to this cylinder. And there is a way to do this, always conformally, to glue a cylinder to another cylinder. And you can choose somehow the height of where the cylinder maps to the cylinder. You can translate them a little bit. So what we're going to do is to glue them so that the orbit of the critical point, so something missing here, so you have the orbit of the critical point hitting at some point here, and you're going to glue it so that this critical point glue to a ray here. Okay, so if you think what we are doing, you are making this critical point, iterating, going through a petal that is missing here, attracting petal, and this point is going to go through one of these rays here or one of the rays here, depending on which one you glue to which one. Okay. So what you do, you cut. So what you're going to do is first fix some of the fundamental domain here. Yeah, so this is a drawing corresponding to this flower with the 2 other ones that are there, and the 3 other ones that are in the back region. So what you're going to do is first to cut some part inside, yes, and just keep from one fundamental domain, and you're going to glue one cylinder to another cylinder, one croissant to another croissant, and doing the same all around this curve. And if you glue it together, you can check that at the end of the day, what you get is something that looks like this. And all of the parts that you have been cutting just disappeared. And you can get a Riemann sphere like this. Okay, so the idea is to do this and to define it something as the pre-images, okay, and say that this is going to be realized as a polynomials. And these polynomials somehow are going to have the critical point going to a ray, so the critical point is going to escape. So what is the difficulty of this? Is it when you do this kind of stuff, the thing is not nice and conformal. Okay, or you can try to do it as a pre-image, etc., and it's complicated to get something conformal. So the tools to be used here are the Thurston theorem or Thurston-like theorem. I think that you have a topological map with something like that looks like conformal, but it's not all conformal. And this kind of theorem, of Thurston theorem, says that these are realized as maps, okay, as conformal maps. So it's another very important tool. Like all of the Thurston-like theorems are very, very important to make by hand some dynamics. Okay, so what I did is to try to do this by hand for degree 4. So I took all of the Hilbert trees with the periodic 4 points, and I perturbed them. Okay, and I've been able to find all of the trees that arise in the case of pair 4, okay, on the curve for period 4. And so somehow by hand you can prove this in 15 minutes, knowing all of this theory. You can prove that pair 4 is irreducible, just doing this by hand and checking the combinatorics, and by hand labeling the trees and checking that these are all the trees given by DeMarco and Pilgrim and Schiff. Okay? So this was something that I observed during my PhD, and I tried to write this later than my PhD, and somehow I get delayed in the time and never finished to write this. But this was somehow the first formal proof of the connectedness of pair 4. Okay. So I try to do this for pair 5. So there are more trees to look at, more Hilbert trees to look at. You have to jump a lot, and at the end of the day, you think that enumerating the things, you're gonna miss some tree. And at this time, I was visiting Jan in Chile during my PhD, or maybe it was a bit after during my postdoc. And we had some free time, and I said, "Oh, Jan, do you know how to find this tree? Is there a way to find this tree? Is there some dynamics that you can perturb to get this tree?" And this is how we begin all of our work on pair n, and get at the end to a formal proof of the reducibility of pair n for all n. Yes, that's it. Getting checked. It has been published. It's not published yet, but it's over review. Okay. So that was one of the first way to travel between escape components. And with Jan, so one of the first work we did before together, when we're looking at this, is we found another idea to travel between escape components. This is something I'm going to talk about right now. That you think about, you have these 8 pictures. So you have a critical point that is escaping, and you know that at some point it's going to be going to have an 8 picture here, and within the two side of this, you have the critical point, which is periodic, because the periodic critical point is within the field Euler set. Okay, so you have such a picture, and you have you look at the image. So instead of putting the image outside, I put it on a separated picture on the right, where you have the image of A, and you have this circle, which is the image of the 8. That usually is around here, yeah, where is the image of minus A. So let's begin by taking a curve like this that includes that goes around the n minus 1, a plus n plus 1, sorry. And there is a way to do this so that when you look at the pre-image, you're going to have two gray regions here and another one which is going to be there at the co-critical point. And so that you have this picture with this one not touching this one. Okay, there's a way to do this, that you can have this. And you can take an annulus in here. You're going to have like 8 type annulus here and another annulus there. So let's forget about the one on the left because not interesting for what we're talking about. And the way to somehow move in my space or transform this is to compose the map in here with a twisting. So what is a twisting is, so you have this annulus, you have another curve which I draw here, and you're gonna push somehow this curve all around this picture. So an intermediate step is gonna be this one, and when you did the twisting that you wanted, you're gonna have this picture. Okay. Somehow there is a way to push this continuously from here and to go around in here. So what you do is that you say that you transform your map. So if you're not in the annulus that we were talking about, then you say I'm doing nothing and I'm not touching polynomials. And if you're within this annulus, then you post-compose by this pushing deformation, the twisting path, the twisting deformation. Okay, and this gives you a family of deformation of polynomials, and this gives you a family of polynomials. Okay, so what happens is if on the left you have this picture, okay, so you have this picture and you take the pre-image, you have the 8, and if you do nothing, then this thing is gonna look like this. But after pushing, you're gonna have a picture like this, which if you can look at it, it's gonna be kind of very weird. So let's make another picture. So if you begin with this picture at the beginning, and after doing the twist, what's gonna happen is that you're gonna have this picture. So your 8 that is blue on the left and red on the right, you're gonna be again a blue picture. But what happens here is that the black point, which is an orbit of the periodic critical point, change of side. So somehow it was on the left at the beginning, and at the end it is on the right. Meaning that if these are polynomials, then the critical point change the side of the 8 level curve. Okay, so somehow the escape component corresponding to this one is not the same escape component as this one. So we are very happy because we made like a continuous move from one escape component to another escape component. Okay? By doing this transformation of pushing things, composing by twists, etc. So what is the problem in here is that all of the things that I'm drawing here are not polynomials. So I begin with the polynomials, but when I'm making some continuous deformation here, nothing tells me that I can do this conformally. Okay, somehow all of this is like doing this, saying that I'm in another space, not of polynomials, but of something which are continuous map of the sphere. So this kind of things, there is a result by Raissy talking about this kind of maps, which looks like polynomials, but which are not. So for this, she introduced a set of topological polynomials. So it looks like polynomials, but it's not polynomials. So you can check exactly what it means, but I don't want to be too formal. Yes. And so there is a theorem by Raissy in her book that says that the path within two polynomials of pair n in the space of topological polynomials. So what I did is I come from pair n and I go to pair n, and I have a path that goes through a bigger space, which is space of topological polynomials. What you say is that this path is homotopic to a path within the curve. It means that you can push continuously this path. so that it stays, this path stays in the curve per end. It looks like a very abstract thing, but for us it's kind of interesting because I say that if I connect two polynomials going through the polynomial to the topological settings, then I can connect them on the curve. Yeah, so being able to make a path from something like this to something like this, which belongs to two distinct escape components, you can say by these abstract results that you have a path within the curve that makes this. Yeah, maybe the dynamics is going to be different and these kind of things in between. That at the end of the day, you've been able to go from one escape component to another escape component. The remark is that this kind of result does not work for rational maps. And one of the big problems, yeah, well, let's talk about this. So another point is that, like this point is tampoco. This point is not a polynomial. The end point is also a continuous transformation, so you did not get a path from the curve to the curve within the topological setting. You get a path from something conformal to something which is continuous, but you're not on your curve so that you can apply various results. Okay. So there is a way to adjust this, is to introduce semi-rational map, which are something introduced by Sweetan. So you have to check some special settings that are going to be satisfied in my case. And within this, you can say that somehow what you have, which is a semi-rational map, can be connected within the space of Raissy towards the curve. So there is a way, what I'm saying, is there is a way to deform this so that it gets conformal, that you are not losing the combinatorics. Okay, and this is something that is done by Sweetan and Jian Zhang. Okay, and how do you do that? You can see that the theorem looks blah blah blah, but it says Thurston obstruction. So again, this is like a Thurston-like kind of theorem, like generalizing Thurston theorem to special cases, which are more general, but there's some restriction, of course. Okay, so using our deformation together with this theorem, we're able to make a path from something conformal to something conformal in two distinct escape components. And with the theorem of Raissy, you are able to say that you can realize this as a path on our curve. Yes. So this work, of course, has been done with Inicio. Okay. So what is a big problem of this is that after we tried to publish this paper, my director of thesis, Xavier Buff, found a gap on the proof of Raissy results. So this theorem of Raissy is still not proved, okay? And this is something that already some people have been looking at, and somehow this to complete the proof here is a difficult question. And it's all about talking about iteration on Teichmüller space, like certain like arguments, yes, certain obstruction, etc., etc. Okay, so this is a big part of holomorphic dynamics to look iteration on Teichmüller space to solve this kind of, to be able to prove this kind of results, which are very powerful. You see that with this result, we're able to prove very easily that the curve is connected somehow. Okay, and the other problem is that these paths that we create are not very constructive because we construct them within the set of topological polynomials, which are not conformal, and the theorem of Raissy says that you can realize this within the curve, but does not tell you anything about what's going to be the dynamic along this path. So you say, yes, there is an abstract way to go from one point to another point. You have a path, but you don't know what is the dynamics of the element on this path. Okay, if you remember the talk of Araceli Bonifant, she was like looking at some spatial rays on the parameter space. And somehow these spatial rays, you know exactly what is the dynamics on these rays. Okay, you can say, talk about critical portrait, you can say a lot of things and tells you about the structure. So somehow to have something which is not constructive may be helpful to prove that the set is connected, but does not tell you about the full description of the space, the dynamical structure of the parameter space. It tells you that you have an escape component at one side that can be connected to another component on another side. But for example, it does not tell you, as we did before, that the two escape components have a common point in the boundary, for example. It does not tell you anything. Okay? But it was a very, very cheap proof if the results of Mary's were proven fully. Okay? So I have some time, so maybe I'm going to talk about some of the stuff which I'm currently doing with Yankiwi, observing what we did before with intertwinings. So somehow going through the intertwining points tells me a bit more about the dynamics, because as I tell you, when I go through these rays, perturbing these points, I'm able to tell everything about the dynamics, because I'm able to talk about the macro trees, etc. So this is something very interesting, and I'm gonna try to say more about the structure of the parameter space. So there is another conjecture in the first paper of John Milner, which is interesting. That begins talking about Hilbert trees. So I remember that the Hilbert trees are the convex hull of superattractive cycles. So you take quadratic polynomials, you take the orbit of the critical point, which is finite orbits, and there is a way to define dynamically a nice definition of a natural tree to look at. That is the convex hull of these points. Okay. So what does Milner says is that you can, if you take this tree and you cut along this tree, so you take, in this case, you have a tree with just two vertices, this one and this one, which correspond to critical point of period 2, the basilica, and you cut along this, and you open this, so you can have a hole somehow. So you get this picture that I stole from, I think both of the pictures I stole them from Milner's papers. And what does he say is that this kind of cut open Gela set appear in the parameter space. So this below correspond to the parameter space for period 2, S2. And you can see that the blue picture, which is above, appear in the parameter space below. That's a conjecture of Milner. So for example, in period 3, you have a polynomial of period 3 on the left, which is called the rabbit. So you have in yellow, you have a period 3 critical point. You have to add one more point here to have the Hilbert tree. And you can cut this and open this. And of course, if you cut this and open this is going to give you a circle. And you can check that this picture black appear in purple in the right picture, where you have these things that correspond to cut this and open it. Okay. Another way to do it, for example, is the airplane. So you have the airplane we were talking about before, period 3 critical point, and in this case you have this Hilbert tree. You can cut and open it, and you can check that you have this picture also in the parameter space. Yes, you have to think that this is a hole here, and you can check that. Yeah, quite harder to see in the case of the rabbit. Okay, but you have this also in here. In period 4, as you will remember, period 4 is more complicated to look at because you just have like local pictures. Okay, so it's much more complicated for higher periods to check this visually. So what is the main idea to begin this the proof of this conjecture that we are looking at is that for the rational rays, so as I said, the blue region looks like a disk, okay, and there's an efficient way to make this look at this disk minus a point at infinity is through very natural, through the Butcher coordinate, etc. So already I was talking about this a little bit. I don't want to be too precise because it's quite late already. But there is a natural way to define rays in this space, which is dynamical way, and you can look at the ways that have rational angles. So somehow it's not difficult to prove that the ways with rational angles length. I think that Araceli and Jack made them in the paper that we're talking about. And we proved it also with Yankiwi. So most of this stuff is like traditional stuff that is already done for quadratic polynomials in Orsi nodes that is adapted to the case of cubic polynomials. Okay, so it's not like surprising that these ways are learning. And so what I'm doing is saying that somehow some of these ways are interesting because they lead to intertwinings. In the case where you have a periodic angle, and in case of pre-periodic angles, they look to other stuff, other polynomials that are well described by Minor, which are called n-ramification. Kind of the same idea. You begin with a quadratic polynomial, and from this you create a cubic polynomial with in this case, a pre-periodic critical point. Okay, you can check this in the first paper of Minor. I think it is in the first paper. So what I'm gonna do is say that both of these things, you can create this by hand. And what I'm gonna do is, let's fix, for example, the airplane, fix a landing point of the ray, a rational ray, and say that you're gonna, for example, if it is periodic, you're gonna create an intertwining at this point by cutting and opening. We did that before, okay? So we cut and open, we put another Julia set, and you get a cubic Julia set. Okay, and then you perturb this so that the airplane still goes on. So you can check that the airplane is still here. And somehow we have to way to perturb this. So this is gonna give you two parameter rays. Okay, you can do this, sorry, for, yeah. So you do that for all of the points which are landing point of rational rays. So if it is a periodic ray that you're gonna create an intertwining. If it is pre-periodic, strictly pre-periodic, then you're gonna make some other thing which is called an ramification. And against this ramification, you can perturb them so that you keep the airplane. And with this, you describe rays in the parameter space. So for example, in the case of the rabbit, you consider some ways that trying to which are periodic or pre-periodic, and you create some rays in parameter space that goes through the component where all of these polynomials here in the blue region have a arbitrary, which is a rabbit. Okay, and you can do this by hand and check that the result of Milnor is true somehow, but what is missing here are all of the rays which have a real angle which is real. So this technique does not work for reals, and you have to think about some other techniques to look at this. Okay, so these pictures. This is, for example, the case of the airplane. So as I said, in the parabolic case, you can have you can do this by intertwinings and parabolic perturbation. What I did with Tsui or from the Orsi note with the paper with Yankiwi. In the Mizurevich case, meaning pre-periodic case, you look at a ramification of Milnor, and or you can do with idea of Timorin of Tsui-Guijan, which is basically the same kind of technique that I was using before, doing Tesh-Muir iteration and certain like theorems. Okay, or you can do it by using old stuff, which are called the Orsi notes. That is something that we are describing in the paper with Yankiwi. Okay, so these techniques are already here. I said Orsi notes when I say Orsi notes, I say Yankiwi, but also John Minor and Araceli Bonifant did this technique. Somehow I believe that they did that before us, maybe. Okay, so there is no. I don't want to appropriate the results because I believe that they did it before me, just that they are a little later to publish it. So, and so for the way which are not periodic, we talk about the real lamination, the real angles. So there are some steps that can be used similar to the other things that I've been doing, which are in the case of non-recurrent rays. There is some generalization of the techniques of Tsui, which is done by Zhang. There's another approach which is using Euclid parapuzzle. Yeah, the parapuzzle. I think that Pascal Roche talked about these kind of things, the motions or the kind of things using puzzles. Well, and somehow what we try to do now with Jan Kiwi is to try to use all of the old papers of Jan about real laminations that is talking about exactly about this kind of things, like saying lamination, what are doing the angle for rational angles, and you want to know what's going on for the real ones, which are not rational, the irrational ones. And so there is a lot of work done by Jan Kiwi about talking real lamination, etc., and see what we are looking at. Some open stuff, and I want to talk about stuff because there are a lot of students and they may be interested in, is to try to, so everything we are doing here is talking about when you have a rabbit or an airplane, so you have a non-trivial Hilbert tree. There's some escape components where you have a trivial Hilbert tree, meaning that you have just one iterate that is staying on the side of the big 8. But we may have to precise this a little more, but there is not like very rich dynamics. And somehow the border of these escape components are like totally abstract for me. So it's very hard to understand what are the things that are in the border of this escape component. Somehow in the rabbit one, so here you can see that you have a rabbit here. You understand that there is a rabbit, there is some structure and coming from the rabbit, and as I was saying, it's mostly coming from end ramification and intertwinings. But for the one where you don't have like a significant quadratic dynamics, like the one outside here, you don't understand what's going on in the border of this one. Okay? So one of the things that Jan is going to talk about is that what we proved together is that in the border of this escape component, you can find some special type of dynamics. So there's a way to find one hyperbolic component of a special type. I don't want to talk too much about that because Jan is going to talk a lot of this. So we're able to find something that is enough for us to prove the conjecture of Milnor. And it's kind of a hard duty. It's kind of hard work to find this one. But somehow we have been kind of lucky to find it. And because we don't understand anything about the dynamics in the border here, it's kind of difficult. And it looks like a good exercise for someone to study. Okay, I don't think it's a very easy problem. And that's all. So thank you very much for your attention. And thank you.
Okay, thanks for the wonderful talk. I think, yeah, are there any questions in the public or? I think, yeah, everybody can speak by the microphone, I think, yeah. Okay, I kind of have like, sorry, was there a question or? Okay, so I have one not so mathematical question. That Helsinki was Peter Helsinki or? You mentioned a Helsinki in your results.
Peter, see.
Okay. I just wanted to check that. It's just that I know him as a geometrical theorist, not as a.
Sorry, lots about the parabolic things, and he had a lot of works on complex dynamics. I mean,
Yeah. I just saw that. Yeah, that he had also that kind of thing.
And many distinct stuff, many distinct topics in holomorphic dynamics. So no, I think no, he's not working a lot on complex dynamics, but he made a lot of work.
Exactly. That's why I was surprised. I know most of like recent work. But okay.
Maybe you want me to explain what is this sentence at the.
Okay. Yeah. That's also.
There is an expression in Chile. So when a guy just talk too casually to a girl and like if you know her, usually she said, "Ni siquiera me invitaste por un pisco sour." It's a nice expression about something that is joining Peru and Chile, like pisco sour things. That made me come to Chile more often when I was a student, and at the end of the day, I finished here.
Oh, that's nice. I have actually like a question, but I'm not as I'm not an expert. I'm just going to ask it. You mentioned something about first theorem about something that is conformal, that you can get conformal stuff. Like, could you specify what you meant a bit about that? Or
so, if you look at a map on the Riemann sphere, which looks like something conformal, meaning that you don't have like all region mapping to points, or somehow locally it looks like Z to the D.
Okay.
And it's well defined, not constant on this kind of thing. Branch covers, these are called topological branch cover. So there are some conditions so that you can realize them as a conformal map. So this is like a super theorem, because somehow you want to say, this exists, so you do it by hand, you make it like by hand, and saying you do it topologically. And conditions to look at, which are not that easy and very hard to prove. Like there's not a way to say I'm going to prove it very easily, but in many cases it has been used to construct by hand some conformal maps.
Okay.
And like this is what I did in 2 occasions here. So when I was pushing the thing from one side to another by hand, I did this by hand. So I was which are not conformal at all, and both the theorems, certain like theorems, or a lot of generalization of the theorem, make me this being a conformal map. Also, I was using it when I was doing the parabolic explosions. So I was cutting and patching things together, and somehow you can define this. You cannot define this homomorphically on the sphere, but you can do it like you can complete this as the pre-images using some continuous deformations, something like this, to say, it's something which is not conformal everywhere, but mostly conformal, and for sure it's going to be topological. Then this kind of result say, yes, you're going to realize this as a conformal map.
These maps are, this condition is not quasi-conformal. It's something topological branching you mentioned. It's
Teschmüller theory, and so it's another tool. Yeah. So what I wanted to use in my talk to there's this family of things doing surgeries and quasi-conformal surgery where you define a complex structure, etc. And there is a family of people that are doing things with certain like theorems. And both of them are still kind of open. There is a lot of work to be done here. And I mean, these two theorems, these 2 point of view on the dynamics made the holomorphic dynamic what it is right now. Like a lot of people working on it and interesting results going on, because these theorems are very powerful. Because if you want to create something which is conformal by hand, I mean, it's very difficult, very complicated. If you're able to do it by hand, you make a picture and you push it here, as I did here, and it looks like easy. Of course, this is not easy because you have to prove that you're in the condition of the theorem, you have, or someone extends the theory to your case. There is some hard stuff to be done, but this is what people are doing a lot.
Yeah,
It was just
Okay.
to motivate you to look at these kind of things. Yeah. In the theorem,
Yeah.
what I've been talking about in this talk is like things that is not all, because we have the talk of Jan Kewig that's gonna come, that's gonna tell you how to do that the right way. But just to introduce some techniques that you heard about things, and you can try to look at this and ask.
Okay. Okay. Thanks for the answer. Are there any other questions? By YouTube, maybe, or just to check? No. Okay. Okay. Then okay. I think yeah. I should thank you. Thank Matthieu. Thanks for the talk.
For inviting me.
And yeah, I think thanks to all, and yeah, we should be finishing right now. Yeah, the call these days, at least, of the conference. So yeah, see you all. Have a good evening / afternoon. Yeah.